Good morning, Astronomy 1020. It's Thursday, it's raining. It's time to learn a little more about the nighttime sky and the orbits of planets. We have our usual hour-and-a-half lecture, followed by homework number 2, which we are going to do together. If you look under homework 2, you can get those questions handy and ready on a separate tab of your computer. Let me get the good marker here and we'll get right to it. Okay, at the end of our last lecture, we learned about different types of stellar coordinates. And the two systems we learned about were the horizon system and the equatorial system, which serve slightly different functions for identifying the positions of stars in the sky. I was going to start with some notes, but I always like to start with a slide. Let me find a particular slide that I'm thinking about that's going to guide our thinking here. It's the one that shows the rotation of stars in the local sky. Boom. Here we go. So this is slide 79. This picture is a model of your local sky, and it's actually kind of appropriate for our latitude in Rhode Island. Do you guys remember what the latitude of Rhode Island is, Providence is?
40-something. Like
40-something, Chris.
42, 43.
42. The answer to life, the universe, and everything, if you are a Hitchhiker's Guide to the Galaxy fan. So our latitude is 42 degrees north. And because 45 degrees is half of a 90-degree angle, we're approximately halfway up the globe. We're at a good medium point between the equator and the North Pole. So our sky is pretty normal, pretty typical for a northern hemisphere observer. And the green disk, of course, represents the grass. And these colored tracks that you see here are star tracks, or diurnal circles. We can follow stars as they rise in the east, come up above your horizon. At the highest point in their journey, they will cross your, man, if only I had a good vocabulary word to describe this thing. The kind of arc that goes from north to south and cuts the sky in half. If only there was a term that I could use to describe this thing, then I wouldn't be so ignorant of the nighttime sky. Can anyone think of a term like that would describe that? You know, the north to south, what do you call it?
Meridian.
Oh, right. Yes, of course, the meridian. The stars will hit the meridian at their highest point in their journey through the local sky, and then they'll sink back down and they'll set in the west, okay? These tracks, these so-called star tracks, are actually tracks of constant declination. Does anyone remember what, hold on, I want to hide the trolls here. I only want to interface with people who want to interface with me. That's how I am. Let's see if I can do my video settings here. Hide the trolls. Okay, cool. Now I'm looking at real live humans. Humans, what's the definition of declination? Maybe we should start by reviewing the equatorial system. Anyone remember what declination is?
Degrees from the celestial equator.
Okay, Christopher, I like your words. You talk nice today. That's good. So look here. What would be the declination of this red ring then? Can you put it into practice? What's the declination of the red ring?
Would it be 50.6?
No. The declination, which Christopher reminds us means degree. Oh, someone's busting in a chat. Let's see what the chat's got to say. Arunsak, he knows what's up. He may be hiding with the trolls, but he is ever vigilant. And he's reminding us 0 degrees because, Christopher, that red ring is the celestial equator. Does that make sense to you? Like, if this is the north celestial pole, that's the direction that Earth's north pole is pointing. And the celestial equator is the red ring because it's kind of perpendicular. Contrast slide 79 with slide, oh, I don't know, was it? Hold on a second here. I'm going to just guess a random number. 42? No. With this picture here, you can see the celestial equator is the red ring that you see there. So, okay, what's the declination of this point right here?
Would it be undefined?
No, unfortunately, its right ascension might be undefined, but its declination is not.
90.
Positive 90, but yes, Christopher, you are correct, positive 90. So Christopher, while we're talking, could you give me some reasonable guesses? If you had to just guess a number, what would you say the declination of the blue ring is? Oh, did we lose your audio?
I would guess 33 degrees.
Yeah, I would say that that's a totally reasonable guess, Chris. If this is 0 here, and if this is positive 90, this looks like it's about 1/3 up the way. I would have guessed 30 degrees because that's 1/3 of 90, but 33 is a very reasonable guess. What about the purple ring? What would you guess the declination of the purple ring to be? I could talk to anyone here. Anyone chime in?
60?
Positive 60. Yeah. Okay, cool. So let's go through this together. So 0 degrees, positive 30 degrees, positive 60 degrees, positive 90 degrees. Keep going. I need to drive this point home. How about the orange ring? What's that declination?
Negative
Negative
30
30.
degrees.
Negative 30. The yellow ring?
Negative
Negative
60.
60.
Good. Now you're learning how declination works. Remember, declination is oriented towards the celestial sphere, right? Right. The celestial equator is 0, and then it goes positive and negative from the celestial equator. But if you're at some arbitrary latitude on Earth, the celestial equator is kind of tilted in the sky. Now, our goal is to be able to go back and forth between the equatorial system and the horizon system. Equatorial system measures things with respect to the celestial equator, but the horizon system measures degrees above the horizon. Remember that the horizon system, let's see here. Let me just check that chat. Jinx, nice. Okay, the horizon system, is it 47? The horizon system measures your degrees above the horizon, and that's altitude. And azimuth measures your degrees along the horizon clockwise from north. I think we got to try to play a little game here so we can kind of lock these concepts in. I'm going to teach you how to draw an important picture, an important diagram. Like our three-dimensional local sky, it's sometimes helpful to make a 2D view of the Rhode Island local sky. And this picture here will help you keep your brain straight if you have to answer a tricksy test question. I just opened a fresh, oh, there we go, fresh one. Okay, a nice fresh marker here. Okay, grab that ruler. It's time for us to leave some headroom. Got to do some drawing here. Leave some headroom for your dome. You might want to make your line about 12 centimeters on the page if you have a ruler handy. Make your 12 centimeter line and then just mark the midpoint with a dot at 6 centimeters. And now make a 6 centimeter line straight up. This is going to be where your dome goes. Okay, in fact, I'm just going to go ahead and draw a line there. And I'm just going to put in a few more dots. Did I do that right? Yeah. I'm just putting in a few more dots so I can draw this dome in smartly. Is that right? 10, 20. Wow. I am out of it today. Okay. I'm going to go ahead and draw the best dome that I can make with a free hand. Something like that. All right. This is a two-dimensional view. We can shade the ground in if we want. So there's the desert sand. Here I put an observer. Damn it, it's not a very good observer. Okay, can you guys see this? We're going to make a north to south slice of the local sky. Label this as north and label this as south. Now, I'm going to draw in my north celestial pole. That's where Polaris is. I'm going to make a line that goes through the foot of the observer. And I'm going to go some arbitrary place in the northern hemisphere. North celestial pole. Let's remind ourselves that this is where Polaris is. I cannot draw the celestial equator on this diagram because the celestial equator, you will remember, is an east to west phenomenon. It rises in the east and it sets in the west. But I can draw this point right here. That's the point where the celestial equator intersects the meridian. And that is a helpful thing to do. So I'm going to try to make a right angle. Let me get, have I got a red here? I need a red marker. Yeah, here we go. And I'm just going to make a dashed line. This is where the celestial equator goes. And this, my friends, is a two-dimensional view of the local sky. These diagrams can be extremely helpful, and they can help you answer some tricksy questions. I notice that there are 1, 2, 3, 4 angles in this diagram. And I am going to label those angles with the first 4 letters of the Greek alphabet. Alpha looks like a little Jesus fish. Beta looks like a squiggly B. Gamma looks like a squiggly Y. And delta looks like a squiggly D. All right? Alpha, beta, gamma, delta. We're going to play a little game that's going to test your knowledge of the horizon system and also geographic coordinates. Okay? So, once you've got this all written down, I'll give you a second here. Chris, you may have been exposed to this in Astronomy 1010, so we're going to call on you if these guys get really jammed up, but let's have them try it first. It's an important exercise the first time you take an astronomy class. One of these angles, alpha, beta, gamma, delta, one of those angles is a direct representation of your latitude on Earth. I wonder which angle that would be. Maybe Devlin, Star Child, you could read us the definition of latitude from your notebook, and that will help.
Give me a second here. I got a lot of notes.
Okay. Hell yeah, son, you're getting your money's worth.
Latitude?
Latitude. What's the definition?
Degrees north or south of the equator.
Good. So do you, Devlin, or anyone else in our studio audience know which of these angles would best represent your latitude?
No. Would it be the NCP?
Well, the NCP is a
Like
point,
that line though?
but I'm asking for an angle, buddy, you know? Like, it's like I asked for an apple and you gave me an orange. The North Celestial Pole is a point on your sky. That's not, a point cannot be an angle, correct?
So I'm a little lost here.
Oh, that's okay. Well, why don't we phone a friend? Who isn't lost? Is there anyone who understands me?
Is it delta?
Well, who said that? Oh,
Kevin.
Kevin. Kevin, you're not exactly wrong. You're just not exactly right, okay? I know that probably doesn't make a lot of sense, but no, we can do better. Maybe I can help. If you're stumped, let's imagine we drew the Earth at the same orientation as our local sky. So underneath, I'm going to draw a picture of the Earth. Don't move the Frisbee. Okay. Here's the Earth. And I'm going to put an observer standing right there in Rhode Island, okay? And if I'm in Rhode Island, the North Pole, the axis of Earth, should be like so. That's the North Pole, and the celestial equator, sorry, the equator, of course, points to the celestial equator. You notice I'm trying to make it parallel here. So this is Earth's equator. Does that help? Does that help you figure out which angle is your latitude? Not at all, huh? Okay, let's get even more obvious then. Devlin, can you read the definition of latitude one more time?
Degrees north or south of the equator.
Arunsak, you can't guess two guesses. That's not fair. Why not guess alpha, beta, gamma, delta? Then I'll be 100% correct. I'm sorry, Devlin, can you say that one more?
Would the answer be 33 degrees then?
No, I'm looking. Your answer is a multiple choice answer, which could be one of four letters. Alpha, beta, gamma, or delta. And Arunsak, you can't choose two.
It's beta.
It's beta. Star Child to the rescue. How did you know that?
Because if you look below, so the equator moves you forward, and that's 30 degrees forward from where it is.
I don't know where you're getting this 30 degrees from. Forget, the 30 degrees is a distraction. Delete 30 degrees.
Well, okay, so there's four sections that you have there. If you put a line through the center of the Earth, then you would have those four lines, and then you obviously just move that way. I can't explain it. I just
It's
visually
tough to explain.
see it.
That's one of the points that we're learning here. It's tough to explain things. Devlin, let me help here, okay? From your definition, the latitude of an observer is their degrees north of the equator, right? And this angle tells us how many degrees north of the equator. Now, your feet and your head both point towards the zenith, right? And the equator points towards the celestial equator. So your latitude is the degrees between the equator and the foot of the observer. Therefore, your latitude is also the degrees between the celestial equator and the zenith, all right? Let's label that in. This is your latitude. Okay, let's try again. One of these angles, alpha, beta, gamma, delta, is a direct representation of the altitude of Polaris. And here we may want to review the definition of altitude. Or you can guess if you know the answer.
I think I know it.
Oh, yeah?
It's the one all the way to the right. Mm-hmm. Yeah.
That's delta. You are correct. How'd you know that?
Just because it looks like something I would solve in algebra, or I mean geometry.
Okay, well, you have the right answer. That's not a sufficient explanation for me, although it's funny. All of these could look like something you'd solve in a math class, right? That
It's
math.
because it's the closest to the equator.
Not the, you almost had me there until you said equator. Clearly,
So
it's
Celestial equator.
Prime meridian.
Closest to the North Pole.
The
What is-
horizon.
Thank you, G. Hey, who's G? G, who are you, G? Or should I just call you G? I guess it doesn't matter. I can't see you anyways. Yeah, G. Oh, you're a troll today. Okay. Okay, G. Yes. It's the horizon. That's all right. Geez, I got myself distracted here. I keep looking at Austin's bagel, and it's making me hungry. Okay. All right. So listen. The definition of altitude is the degrees above the nearest horizon. This is the closest horizon to Polaris, and the altitude is the degrees up from the horizon. When you answer those questions, you want to, I know, Devlin, me too, the degrees above the nearest horizon. Now, let's put some numbers on this bagel, okay? What is the latitude of a Rhode Island observer?
42
33
degrees.
degrees.
So let's put 42 degrees here. Now, I spy with my little eye a 90-degree angle, between the North Pole and the equator, between the North Celestial Pole and the Celestial Equator. So what does that tell us about gamma?
That it's 48 degrees.
Very good. And yet, I spy with my little eye another right angle. There's always a right angle between the zenith and the horizon, meaning that delta should also be, what should
42 degrees.
That's right. And this is why earlier when Kevin said delta is your latitude, he wasn't wrong. Your latitude and the altitude of Polaris are always the same. Let's flush this out here. This should be a 48-degree angle as well. Now,
Is that why people use the North Star to navigate? Because it always has the same latitude?
Exactly. This is the whole art of celestial navigation. If you are lost at sea and you are in the northern hemisphere, if you can identify Polaris using those pointer stars, you can use a tool such as a sextant. Here we go. Just so happens, of course, that I have a sextant on me. And a tool like this can help you determine your latitude. Let's see, it's been a while. I don't know if I didn't use this model before, but the way this works is there's a little angle, there's a little mirror there, and you can use the sun or you can use Polaris, and you have a small telescope, and you can adjust this until Polaris appears in the telescope, and then read your latitude off this machine. You could also use your hand as a crude angular measurement tool. You know, if this outstretched is about 20 degrees, you can you could do it with your eyeball. You don't need a sextant. A sextant just allows you to take a more precise or more accurate measurement. One of those two. Okay. Actually, both of them, precise and accurate. All right. We've just learned an important result that I want you to write down below. This isn't just about Rhode Island. It's always true that these angles will have this relationship to each other. This will be your latitude, this will be your latitude, and these two are always 90 minus your latitude. So what we have just proven is a fundamental result, which is this. The altitude of Polaris is equal to your latitude. And I think that's important enough where we should put a box around it, and we should put some stars next to it, and maybe even some beams of fire, so that when we need to use this later, you'll be able to find it, okay? You can do things with this statement. You can solve tricksy problems. The altitude of Polaris is equal to your latitude. Okay, let's try a couple more sample problems. We're, of course, going to be working on this in our homeworks today. The homework today is actually rather challenging, but there's a couple of problems in the homework that I think it might be worth talking about now. We'll see if you can remember it later. This is a beautiful drawing. Take a photo of it or whatever you need to do, but I need to erase this in a second. Is there anyone out there who needs another second to work on this drawing? Oh, nice. Whoa, there comes the sriracha. You dirty dog. Okay. It doesn't sound like anyone needs another minute here, so I'm going to erase. So we're going to have a question like this in our homework today. Let's see if anyone can handle it. Suppose I ask the following question. Describe the location of Polaris in the Rhode Island local sky. Of course, Cameron. I always record the homework and it always goes up on the old YouTube. So if you have to duck out early, it'll be there. But remember, we're going to be in the habit of turning in our homeworks by Sunday, right? Cameron, that's the rule. We're all going to try to do that. Okay, awesome. How do I answer this question? What's the answer?
Child, did you ever turn in your homework in your lab?
Did you, Star Child? Did you turn your homework?
I did.
All right, good man.
Not for week 2 yet, just for week 1, but I got
That's fine. I just, by Sunday, so you guys have already turned in homework 1, lab 1, presumably. By Sunday, you will have turned in lab 2, and today we're going to do homework 2, all right?
Quick suggestion. Can I just make one quick suggestion for the recordings on YouTube? It would be helpful to timestamp when you start the homework and when you are done with the lecture. That way, because I was just
people could skip my lecture?
I already attended the lecture on lab 1, so I already had all the notes, and I just didn't know when the
Devlin,
homework.
it's not a bad idea. My original idea was that they would have to watch the lecture and I'd make them click through it, at least if they were going to skip it. But honestly, the real truth is I'm so like inept at YouTube that I don't even know how to put, I'm sure I could figure it out. I will figure out how to put a timestamp on there.
It's not even like you have to just do it for the video. You could just put it in the comments, or I mean in the description.
Oh,
just
yeah.
Like a time of when
Do you guys notice that I try to put the chat log in the description? Because sometimes they're really funny. Like last class's chat was really, really funny. Anyways, okay,
Everywhere.
so, but I'll take that under consideration, Devlin. Maybe I'll try to do a timestamp. That's not a terrible idea. Okay, so point taken. Okay, what's the answer to this question?
42 degrees, positive.
Kind of, but hold on. Here's the idea, guys. We need to use the horizon system. The horizon system is how you describe the position of an object when it's in your local sky and you want to point to a friend. But remember that the horizon system requires 2 angles. I need an altitude and I need an azimuth. So when you say 42 degrees, which one of these are you giving me?
I think the altitude, correct?
Correct. The altitude is 42 degrees, and you know that because you just learned that the altitude of Polaris is equal to your latitude. But what about the azimuth?
Wouldn't that be 90 degrees?
No, not 90 degrees. Remember, azimuth is similar to direction, right? And 90 degrees, Kate, if that was you that I just heard from, 90 degrees is east. But we're talking about the North Star here, not the East Star. So what would the azimuth of north be? Zero degrees, says Devin. Devin is correct. 0 degrees, or we could say north. Sometimes for an answer, you can just substitute. Yeah. Oh, no, hold on, Devin. I want to talk about due north. Let me show you in a picture here. If if a person says due north, what that usually means to me, due north means here, north in azimuth, but directly on the horizon. Since Polaris is up here, I would not say due north because that implies that the azimuth is due north, but I usually avoid saying due unless the star is on the horizon. It's a small quibble, but maybe you can understand where I'm coming from there. I just paused something. Never mind. Okay. So our answer was an altitude of 42 degrees, azimuth of north. So what you would do is you would go outside at night and you would take your laser pointer. All right, I've got star laser pointer, and you'd start on your horizon and you'd go up about 42 degrees, which is kind of like a halfway up to the sky, and you would look halfway up the sky directly north, and there you should see Polaris. You could even try that tonight. You could use that compass app on your phone. You could stand outside and well, it looks like it's kind of rainy today, but next clear night, if you're out at the beach or something, you could use the compass app, figure out which way is north, go halfway up, see if you can find Polaris. And remember, students, you can use the pointer stars. Share screen here. Let's go to slide 80. Let's see. Oh, wow, that was amazing. I just called that right up. Okay, so the pointer stars allow you to find Polaris. You use the front two stars of the Big Dipper. So that's another way that you can do this. All right, let's try a slightly trickier question. By the way, that's in our homework today, so we're actually doing our homework.
Isn't Polaris the brightest star in the sky, though?
Hell no. The brightest star in the sky is Sirius, the dog star. Sirius follows at the foot of Orion. But there are many other brighter stars than Polaris. Polaris is actually kind of like actually something cool about Polaris. Later on, I'll teach you about variable stars. Polaris does not have a fixed radius, but it actually pulsates over the course of a month. So Polaris varies from a second rank brightness star to a third rank brightness star over the course of a month. And if you do a little observation log and keep a journal, you can notice that yourself. Okay, I have another question for you guys. Well, Devin, that's a cool question, but if you mean ranking in terms of the magnitude system, the sun is so much brighter than the other stars that its rank is -27. That sounds probably really confusing. You're not ready for this yet. If the sun were located 10 parsecs away, which is, if the sun was approximately at the distance of, say, Sirius, our sun would be a 5th rank brightness. So our star is not one of the brighter stars out there. It's medium to dim, okay? So our star is a garden variety ordinary star, ain't nothing special. And that's how we like it.
A parsec is a real measurement?
Weak. But yes, believe it or not, this system, which you are going to learn eventually called the magnitude system, is a method of ranking the brightnesses of stars by the human eye. It was invented by the Greek astronomer Hipparchus, and we still continue to use this magnitude system today for complicated reasons. Okay, here's question number 2. Question number 2 is, describe the path of the celestial equator in the Rhode Island local sky. This is going to be a little trickier than the previous answer, although you guys did just fine. Let me first point out, and this is an important point, no pun intended, it's an arc. It's not a point. And to describe an arc through the sky, you actually require 3 points to properly describe its trajectory. I refer to these points as the rise, the reach, and the set. And here's something kind of irritating. Each of these points, rise, reach, and set, will require their own altitude and azimuth. So we're going to need a set of 6 numbers to properly do this. So there's a point where it rises, where it reaches, and where it sets. Let me use the drawing to help you through this here, because I can imagine that's tricky. Share screen, and it was 47. Whoops. It was 47. All right. So let's come up with a nice color here. I've been using orange, but I think I want to use magenta. Okay. So my idea, and I'll use the little dot tool, this point here, usually things rise in the east. So this is the point where the celestial equator rises. This is its highest point. That's the reach. And this over here is where it sets. Those 3 magenta points are the points we're trying to describe here. The rise, the reach, and the set. Does anyone want to try to tackle one of them? You might start with the rise point. Okay, what do you think?
All right. For rise, I think the altitude is 0 degrees.
You are correct, Christopher. What about the
And
azimuth?
that would be 90.
Very good. Or we could say east. So it's 90 degrees or east. And here, if that was Devin, here we could say due east, because that point is on the horizon. That's unambiguous. Okay, Christopher, you killed it. How about the reach? Maybe we need to look here. Maybe we need to remember the alpha, beta, gamma, delta game for some help. The reach is this point here.
I'll try it.
All right, hit me.
Oh my God. Is the altitude 42 degrees?
Not 42.
Is it 48 degrees?
That's right, because remember the angle from here to here in our local sky, that's the latitude. So this is 90 minus latitude. So the altitude is 48 degrees. What about the azimuth?
Well, that must be 0 degrees.
No.
Wow.
Azimuth is measured clockwise from north.
Okay. Well, okay, we can do that. Clockwise from north would it be 180 plus 48? 228?
Whoa, hold on. The 48 is the altitude. Leave that out of it.
Okay.
But let me help here. Go back to the picture. This is your azimuth, right? Degrees measured clockwise from north. So what is that angle?
So that's 180.
No cuts, no butts, no coconuts, all right? Just 180.
Oh, straight up? All right.
Or we could say south. South is the closest point on the horizon. How about the set point?
Would it be 0?
Wait, which one? Be very explicit here.
Altitude?
Correct? Oh, I can hear the parakeets, or what are they again? Cockatoo? I can't remember. Are they parakeets?
What was that?
I can hear your parakeets. Are they?
Oh, yeah.
Is that what they are? Parakeets?
Yeah.
Nice. What's the
And then-
azimuth?
Would it be 90 degrees west?
Careful. Clockwise from north. So this is to go clockwise from north, you start north, right? Give me that pencil. And you go clockwise from north. How many degrees is that?
$180.
There, no. Oh,
270.
Oh, 270.
270, that's right. Okay. Looks like some people had it in the chat. G knew what's up. Okay, so this is 270. Or west. And that's due west. Now, this is the technical description to the answer. 0 degrees altitude, 90 degrees azimuth, 48 degrees altitude, 180 degrees azimuth, 0 degrees altitude to 70 degrees azimuth. But there's also a literary way to say this information that's kind of classy. You could have also said the celestial equator rises due east, reaches 48 degrees in the south, and sets due west. What's cool about this statement is this is a classy way to say the answer that contains all of the specific power of the horizon system, because you are giving a rise, a reach, and a set, and it's completely unambiguous. Keep in mind, the reason why we want the horizon system is so that we don't say silly things like, it's to the left of the pine cone on the tree over there, just above your house antenna or something. You know, you can't talk like that because it's confusing. But if you say, this is where it's going to rise, altitude and azimuth, this is where it's going to reach, that's where it's going to set. That's a pretty unambiguous description. Suppose I really wanted to like push you guys to the limit and I asked you some crazy questions. Like, suppose you go to the North Pole. Where's Polaris in your local sky? Austin? Austin knows.
Is it right above your head?
That's right, it's at your zenith. Because your latitude at the North Pole is, Austin, what would your latitude be at the North Pole?
Your latitude at the North Pole.
G's got you. 90 degrees north, G. You have to specify north, too. And that means the altitude of Polaris is 90 degrees, which is, anyways, Austin understood it was at your zenith. Okay, no, that's good, G. What if, by the way, all right, what if we went to the equator? Where would Polaris be if you're standing on the equator? Here comes the kitty. Here comes the kitty. What's Kate? What's the name of that little guy? He's got control of. Hey, what's the name of that cat, Kaitlyn?
This is Banks. She's not very happy with me.
Banks.
Banks, like from Hocus Pocus.
Oh, I didn't see that, but I'll Binks. Okay, Bink like B-I-N-X.
Yeah, B-I-N-X.
Cool. Well, give her a little cat treat or something.
No, she's rich. She doesn't deserve it.
I tend to just watch like really dreary post-apocalyptic science fiction movies. That's the, you know, it comes with the territory here. No, never saw Hocus Pocus, but I got to work on that. Anyways, let me show you a couple of slides here that I think will be interesting, or not uninteresting, as my old professors used to say. Let's imagine going to different places on Earth, and let's imagine how the nighttime sky would work. I think I've got a couple of pictures here. I thought I had a couple. I have a couple of pictures in my astrometry lecture. Bear with me here. Okay. So this is the view from the North Pole. This is from your own textbook, and I think it's an okay slide. If you were to go to the North Pole, Polaris would be over your head, and here's something kind of interesting about being in the North Pole. As Earth spins, stars don't actually rise or set on the North Pole, but stars actually just circle around the sky, which is kind of wild. And that means all stars at the North Pole, all the stars in your local sky, they're all circumpolar. You'll remember that a circumpolar star is a star that never rises or sets. So all stars are circumpolar from the North Pole. We can talk about the path of the sun in a moment. Now, I asked about the equator, and I didn't get any takers on that. Here's what the situation looks like from the equator. Careful here, the sinister left-handed artists like to put north on the left-hand side. That irritates me, but whatever. You can see the observer is standing with Polaris on their northern horizon, and all the stars rise in the east and set in the west on tracks which are perpendicular to your meridian, okay? Actually, the equator is kind of a cool place to observe the nighttime sky, because if you wait long enough, you can pretty much see every single star in the heavens. Unlike the equator, if you're located at some arbitrary latitude, like if we're located here in Rhode Island, there are some stars in the southern hemisphere of the celestial sphere that actually never rise above our horizon. And that's really sad, because there's a couple of really cool magical objects that can only be seen from the southern hemisphere. I've always wanted to see the large and small Magellanic Clouds, which are two small galaxies that orbit the Milky Way, and you can see them with your naked eye from the southern hemisphere. I'll show you pictures of them at a later point, but so it would be cool to be able to do some southern hemisphere observing. We could also talk about the path of the sun, which is actually a worthwhile thing to do, okay? To help you understand what the sun is doing on a day-to-day basis, let's return to this slide here, which shows the path of the ecliptic as a horizontal line or horizontal circle. So here we've tilted the Earth by 23.5 degrees. The celestial equator is shown in red. The ecliptic is the path of the sun over the course of the year. And you see that we've marked out 4 key dates. Let's start with the spring equinox. On March 21st, the sun will be stuck to the globe here for a full day. And as Earth spins, the sun will be stuck to the celestial equator. And that means the path of the sun on that day is basically the same as the path of the celestial equator, which we just described. I also have a picture of that. Maybe not a great picture, but it'll do. On the spring equinox, the sun will rise due east. It'll reach an altitude of, how high will it get? The sun on the spring equinox?
42 degrees.
Remember, 42 is this angle.
180.
There is no such thing as an altitude of 180. Altitudes go 0 to 90. You're talking about the azimuth. Arunsak knows.
48, sorry.
Arunsak called it out, 48. That's okay. We're still learning this, guys. This is really tricky your first time around. So if you don't get it right, don't beat yourself up. This is hard stuff. Okay, so the sun will rise due east on the spring equinox. It'll reach an I should pick yellow. Okay. It'll reach an altitude of 48 degrees and it'll set due west. Let's think about where the sun will be on the summer solstice. On the summer solstice, the sun travels a constant declination of positive 23.5. So on the longest day of the year, in a Rhode Island local sky, the sun will rise kind of north of east. It'll reach a maximum altitude of 72.5 degrees. How did I get that? Think about it. And then it sets north of west, okay? On the winter solstice, the sun will rise south of east. It will reach a maximum altitude of, I think, 24.5. What's 48 minus 23.5? 24. Downtown life. Okay, and then it sets south of west. So this is the path of the sun. Oh my God, shut up! Hey, shut up! Sorry, someone got a little crazy on their horn and I had to tell them to shut the F up. Okay. Path of the sun. That's what I was talking about. Oh, everyone likes the kitty. Now you know how the sun moves through your local sky. This is why you put your plants in the southern window, because they will get the maximum exposure to the sun over the course of the year. What about the planets? The planets move differently. She's sitting on your keyboard. The planets move differently. Have any of you noticed that there's a few planets up in our local sky? Are you the class I was telling about Mars being next to the moon? Did I tell you guys about that? Oh, this weekend I was out walking around and it was very lovely. Mars was in conjunction with the moon. So I think on Saturday night, the moon was here and Mars was like a brilliant red dot directly above it. It looked kind of cool. It was like a neat thing to see in the sky. Night after night, the moon and the planets drift with respect to this background stars. So because of this, they probably won't be in alignment tonight, but Mars, Jupiter, and Saturn are all up in your local sky right now. Do you guys know how to tell the difference between a planet and a star? Did I tell you the rule? What's the rule?
Stars twinkle, planets don't.
Exactly, okay. So let's learn a little bit about the orbits of the planets. I think I've covered all I need to teach you about the paths of the stars. Now I'm going to kind of kick things up a notch, and we're going to talk about some more advanced stuff. Let's start by talking about the planets and try to understand why they are more complicated in their motions than the sun or the background stars. Hey class, how many planets are visible to the naked eye? Do you know? Which planets can you see with the naked eye? These are the almost Austin.
I'd say about 5.
5. There are 5 naked eye planets. These are the planets of classical antiquity. The 5 naked eye planets are Mercury, Venus, Mars, Jupiter, and Saturn. Actually, kind of interesting thing about that. There are 5 naked eye planets, 1 sun and 1 moon, and they all move with respect to the background stars. And that means that there are 7 naked eye astronomical objects that are not stars. And where's the slide here that I'm looking for? There's also, no kidding, 7 days of the week. That's not a coincidence. The days of the week, the 7-day calendar, are named in honor of the naked eye observable objects. The sun is for Sunday and the moon is for Moon Day. And to understand how we got the names of the days of the week, remember that English is a mixture of Latin and Germanic languages. So as Rome expanded northward through Europe, they came into contact with some, Visigoths or some Vikings or some Nordic peoples. And Mars became associated with Zutog, their war god, and that became Tuesdag and eventually Tuesday. Mercury is associated with the Viking god Woden, the traveling trickster Woden, and that turned into Woden's Day and eventually Wednesday. Jupiter is literally Thor's Day, right? So happy Thor's Day, everyone. Venus became associated with Freytag, the love goddess, and that became Friday. And Saturn is still related to Saturn Day. So the reason why you have 7 days of the week is because of these naked eye objects. In fact, virtually every aspect of timekeeping and calendars is related to the motions of planets and stars. The word planet, yes, it's really cool, Austin. The word planet comes from the Greek word planetos, which means the wanderers. So planets are wanderers with respect to the stars. And let me further explain what I mean by that by showing you what it would look like if you were to watch Mars night after night after night. Let's see here. Oh, actually, I should get back to that picture later too. There's many things to tell you. I want to show you this picture here. Okay. This is a picture of what it might look like if you were to watch Mars in your sky right now. If you can look south in your local sky, you may be able to see a part of the constellation Sagittarius. And the part that will be really obvious to you is known to astronomers as the teapot. And no kidding, it really does look like this. It looks like a teapot in the sky. If you're somewhere along the southern coast of Rhode Island, take a look out your window and see if you can find the teapot. Now, if you were to go out and observe Mars, On a particular night, let me get my annotation tool and let me make it red for Mars. You might go out one night and you might see Mars brilliant and red in your sky, and you may notice, Mars is kind of sitting above the spout of the teapot. That's interesting. And if you watched Mars night after night, you would notice that as the teapot rises and sets, each night you'd see Mars shifting in its position with respect to the teapot. A few days later, you'll think, wow, I swear Mars was near the spout a few days ago. Now I can see Mars near the top of the teapot. And sure enough, if night after night you observe Mars, you will see it shifting in its position relative to the teapot. You will see it drifting eastward along the ecliptic. If you were an ancient philosopher staring up at these objects, that would really weird you out, because the sun and the moon also drift eastward along the ecliptic. And it may not have been obvious to early observers of the nighttime sky that these really, really bright objects were not stars. I mean, they eventually figured out that they weren't stars because they wandered. The stars in the teapot don't drift with respect to each other. They stay fixed. And literally, the Greeks and the Romans worshipped these objects as their gods. Like their god wasn't some abstract old man in the sky with a beard who got mad at you when you said a cuss word. Their god was right up there in the sky night after night wandering among the stars. That was Mars, right? The war god. And there was Jupiter, and there was all these other gods that were wandering through the sky. What really messed up the Greek astronomers was this. From time to time, the planets, their gods, would suddenly slow down in their motion, and for a period of about 2 weeks, the planets would begin to drift westward along the ecliptic, and then they would change their mind, and after a week or so, they would drift eastward again. And this totally messed up the Greek philosophers. They could not, in fact, they probably had a certain irreverence for the gods because they thought they were a little bit crazy. This thing that planets do is called retrograde motion. Let's write that down. Retrograde motion is a temporary westward drift made by stars, made by planets, excuse me, from time to time. Understanding retrograde motion is the whole story of how astronomy begins. Greek philosophers, in an attempt to understand their cosmos, in an attempt to understand their gods, wanted to understand the motions of these planets and try to figure out why they would sometimes temporarily go crazy and undergo this retrograde motion. Now, in ancient times, the Greeks, let's see if I have, I don't know, I'm going to have to call up a new slideshow here, guys. So we're going to transition now. Bear with me for a second. I need this. And I also need, sorry, I'm getting confused here. I could also use this here, okay? So we're not going to cover all of chapter 3, which is the history of astronomy. I'm just going to cherry pick a few different ideas that might be helpful. In the ancient world, the Greeks believed that Earth was the center of the cosmos, and that stars, planets, sun, and moon all revolved around the Earth. They also believed that the orbits of planets were perfectly circular. In fact, for Greeks, circles were like heavenly objects, and it was important that the heavens be circular so that they did not become unwound like a broken clock. Their attempts to describe retrograde motion at first were somewhat crude. Their concept of how planets underwent retrograde motion was that planets must somehow be orbiting on a secondary circle called an epicycle, and as that circle drifted, planets could undergo retrograde motion. It was kind of a kooky idea, but it explains the observations, and it made sure that their heavens were circular and centered on Earth. Only after Nicholas Copernicus realized that the sun might be the center of the solar system did he discover a much more elegant description of retrograde motion. Copernicus went ahead and suggested that he could make a simpler model of the solar system if he plopped the sun in the center and had Earth orbit around the sun. He could then describe retrograde motion in an elegant way. It was an effect of Earth passing by the other planets as it laps them in their orbits. So here, for instance, this is the correct description of retrograde motion. Earth can see Mars projected against the background stars, maybe near Sagittarius. And as Earth and Mars move forward in their orbits, we can see Mars is shifting a little bit eastward relative to the ecliptic. But for a few weeks, as Earth goes past Mars, Earth creates a kind of parallax effect where Earth drifts past Mars and sees Mars temporarily shifted backwards or westward along the ecliptic. And then in configurations 7, 8, and 9, both Earth and Mars drift eastward again. So if you put the sun in the center of the solar system, you can naturally explain retrograde motion as an effect of, it's the cause. It's a parallax effect as Earth passes by planets in its orbit. Does anyone know what I mean by the word parallax? Parallax is going to be an important concept in this class. Everyone take your thumb, okay, and hold it outstretched like this, or you can do it anywhere in your room. Hold it far away though, Kaitlyn. Now close one eye and note the position of your thumb and blink your eye back and forth. What do you see happening with your thumb there? Could you see your thumb shift back and forth? That's parallax. It's an angular shift in the position of an object due to, your changing perspective there. Parallax happens not only for planets, but also for stars. It's going to be a big deal in this class. I'll define it later. The only problem with Copernicus's model of the solar system is that he could not accurately predict the positions of planets because Copernicus had a fatal flaw in his design of the solar system. Copernicus believed, like the Greeks did, like Plato and Aristotle did, that the orbits of the planets had to be perfectly circular. And because of this, his model was sort of flawed, and the inaccuracies in his model actually led to a great debate between heliocentrism versus geocentrism in the ancient world. People didn't trust Copernicus putting the sun at the center of the solar system, not only because it was unpleasant for people to imagine that they weren't the center of the universe, but also because his model didn't actually predict the positions of stars and planets as well as it should have. The solution to this problem came hundreds of years later, when a legendary German mathematician and astronomer named Johannes Kepler stole the orbital data of Mars from his professor master and fled to the forests of Germany to redo the Copernican solar system, deviating the orbits from perfect circles and allowing the orbits of planets to become a special geometrical shape called an ellipse. And Kepler is sort of credited with our first correct description of planetary motion. He came up with what are known as 3 laws of planetary motion, and you guys are responsible to learn about that today. That's our last piece of business before our class ends. First, let's have a few words about ellipses. In our labs next week, I'm going to have you guys make an ellipse. You can think of an ellipse as a squishy circle. And the way that you make an ellipse is you take 2 thumbtacks and you put them into a piece of paper. By the way, for lab on Tuesday, you can of course watch me do the lab, but if you happen to have a piece of cardboard, 2 thumbtacks in a string, which are pretty easy enough materials to come by, you can actually do the lab with me and make it really slick. So let me give you a heads up on that now. This would be cool. I know not everyone will do this because that's the nature of things. But if next week, if some of you wanted to be real badass, if you can rustle up just a piece of cardboard, just cut it off of a wine box or something, and get 2 thumbtacks or get 2 push pins actually, and a little loop of string that you tie into a circle, then I'm going to teach you how to make a proper ellipse. And that's on Tuesday. So you've got the whole weekend to come up with these materials. Okay. What we're going to do is we're going to make a crappy model on our papers using our rulers. So let's make a model of an ellipse, and then I'll tell you Kepler's laws of planetary motion. Okay, so let's talk about an ellipse. An ellipse is a squishy circle. And if you have your rulers handy, I'll teach you how to make an ellipse. Make a line 12 centimeters long on your page. And mark the midpoint. Then make a line that's maybe, oh, what's a good interval? Maybe 9 centimeters vertically. I did mine very small, do 20. All right, so make yours 9 centimeters long. And then we're going to kind of cheat, and we'll connect the ends to make a kind of football shape. Well, this is a pretty lousy ellipse, but we'll do it proper like in our labs on Tuesday. Okay. The actual properties of an ellipse, wow, this is one of the worst ellipses I've ever drawn. Okay. The actual properties of an ellipse are that if you tie the loop of string around the 2 thumbtacks, you keep the string taut so that the perimeter of this triangle is always constant, and we're just going to drag our pencil along the page. That's how you make an actual ellipse. We're going to do that for lab on Tuesday. Okay, I need to label some parts of this. First of all, an ellipse has these things called focus points. And you can just kind of wing it. Just put your focus points like here and here. They're supposed to be equal distance from the center. This is focus point F1. This is focus point F2. There are a couple of properties of the ellipse that we want to identify. The long axis is called the major axis. The short axis is the minor axis. That's minor. There's a parameter of importance, the distance from the center to the focus point. In our class, we're going to call that letter X. And X stands for the focus distance, or the focus offset, whatever you want to say. The focus point, or the focus offset, is the distance from the center to one of the focus points. There's another parameter of extreme importance. I'm going to do that one in red. It's called the semi-major axis. It's half of the major axis. And that gets its own letter in astronomy, letter A. And that's because Kepler did that. So A, this parameter, is called the semi-major axis of the ellipse. At first, it just seems to be half of the major axis, But you'll quickly discover that it has much more importance than that. Last but not least, there is a parameter that describes the squishiness of your circle, and that's, or the squishiness of your ellipse rather, that's called the eccentricity. It gets the letter E. Eccentricity is X divided by A bear with me. This is the eccentricity, and the eccentricity can be thought of as the percent squishiness of your ellipse, where the domain of eccentricity, or the range, the domain, is it can be greater than or equal to 0, but must be less than 1. In other words, an eccentricity of 0 is a perfect circle. An eccentricity of 0.5 is an egg, and an eccentricity of 0.99 is a cigar. Maybe I better show you a picture of some eccentricities to help. Are you guys still copying this down? Yeah? I'm gonna refill my iced tea. Why don't you guys finish up that drawing here? Give me a second, I'm dying of thirst. Okay, that worked out perfect. Let me show you some common eccentricities. I want to go to the old internet here. And there's a cute picture of eccentricity. Let's see if I can, there's one that's like a little cartoon. Yeah, this one. This is actually a pretty decent image here. Okay, homework Friday. Chris, good luck at work. Iced tea, yeah. Iced tea with not vodka, okay. Here you go, increasing eccentricity. Here an eccentricity of 0 is a perfect circle. And notice as we go from 0.2 to 0.5, it starts to get egg-shaped. And as your ellipse gets closer and closer to 1, it becomes more oval and more squashed. By the way, the eccentricities of the planets are actually quite low. If we type in eccentricities of the planets, I want to show you guys something. Look at the eccentricities of all of these planets in our solar system. And notice that Earth has an eccentricity of 0.02. Venus has an eccentricity of almost 0. Saturn is like 0.06. Jupiter is 0.05. The eccentricities of the planets are all really low. So although their orbits are technically ellipses, the ancient astronomers had a difficult time detecting it because they were so close to perfect circles as to be almost undetectable. This is why Kepler's laws of planetary motion were such an important insight. He solved this problem where we couldn't predict the positions of planets by realizing that these were not perfect circles, but were slightly deviant from perfect circles. They were ellipses. And now it's time for the big kahuna. This is what we've been building up towards. Johannes Kepler gave us 3 laws of planetary motion in his famous book called Harmonious Mundi. And you guys need to learn and memorize them so that you can take your first step into understanding the orbits of planets. So this thing that we're about to do here is a really big deal. Make sure you take some notes on it. I'm going to erase this. Any objections? Okay, here I go. This will be our final battle for the day, okay? Kepler's 3 laws of planetary motion. The first law is the law of ellipses. The law of ellipses states a planet orbits the sun on an ellipse with the sun located at a focus point. And that's located. Just to drive this point home, let me do you a solid and show you the slide that should go along with this. All right, so here's the idea of the first law of planetary motion. Notice the sun is not at the center of the orbit. The sun's at a focus point, and the planet orbits on an ellipse. Do you guys remember the names of this point here? What do we call this, the closest point to the sun in orbit? Special vocabulary term. Anyone know what I'm talking about? Man, there's a lot of bagels going around today. Aphelion. Sorry, Paul. Paul G. Aphelion is this point, farthest from the sun. So if this is aphelion, APH, what would this point be then? Paul G. or anyone? Does anyone know what the hell I'm talking about?
Yeah, it's a perihelion.
This is perihelion. I'm going to abbreviate perihelion as peri, okay? So that's your perihelion point. That's your aphelion point. By the way, we can calculate these. This is kind of a secret part of Kepler's laws. There's a little formula. Sorry, the sun just got flipped around here. The perihelion is the semi-major axis times 1 minus E. The aphelion is the semi-major axis times 1 plus E. We're going to actually need that for our homeworks today, so let's write that down. So this is a secret bonus, all right? We can calculate perihelion as A times 1 minus the eccentricity, and we can calculate the aphelion as A times 1 plus the eccentricity. So put that in brackets. That's not exactly one of Kepler's laws, but it's a good enough place to introduce those two formulas. Okay. Kepler's second law of planetary motion tells us how the planet goes around the star with time. Let me show you a picture here. In this crummy animated GIF, you can see the planet swooping around the sun, and as it approaches perihelion, it speeds up a little bit. As it gets out towards aphelion, it slows down a little bit. So its speed is not uniform, but it speeds up and slows down. Kepler was such a clever bastard. Look what he figured out. He figured out that if you took a line and you connected the planet to the sun, and then you sort of observed it for a period of time, like let's say this is the orbit of Mars and we're watching it for 2 months. Kepler would realize that in 2 months, Mars might go from point A to point B when it was near perihelion, but that in a similar 2-month period later on, it would only travel a much shorter distance from H to I. But then he discovered that if he sort of traced out the area that the planet sweeps through, if he divided this angle up into a bunch of boxes, that the area of this short triangle was equal to the area of this long skinny triangle. So that even though the distances the planet travels are not the same, the area that the planet sweeps through must always be the same. And that's cool because he could use that to predict where the planet would be next. This is now known as the law of equal areas, or just simply the law of areas. And it goes, a planet sweeps out equal units of area in equal intervals of time. A planet sweeps out equal units of area in equal intervals of time. This is the law of areas. Before I give you the third law, I need to erase. So give me some thumbs up when you're done copying, okay? You good, Elijah? Okay. Emily's good? Stacy's good. Arunsak's good. Who else is out there? Okay, we'll give you a second, Tiff. G's good. Okay. This is good. It gives me a sense of like how long it takes you guys to write these notes down. It's not always obvious to me. Donovan, you still writing? Oh, you're good? All right. Anyone mind if I erase? Anyone still writing? Our third law will be the last bit we do for today, but it's kind of important. The third law is maybe the most important for your homework and for your exam. Kepler's third law of planetary motion is known as the harmonic law. And it's basically a mathematical equation that helps you figure out the period of the planet or the distance to the planet. It goes a little something like this. P squared is equal to A cubed, where P is to be measured in years and A is to be measured in astronomical units. P is the orbital period of the planet, and I'll say it again, measured in years. A is either the semi-major axis, or another way to think about A, it's not just the semi-major axis. You can think of it as the average distance between the planet and the sun. And once again, it must be measured in astronomical units. In fact, believe it or not, Kepler is the astronomer who invented the astronomical unit, and he invented it for this formula. Take a second to jot that down, and then we're going to try a couple of sample problems. We're going to need this for our homeworks today. Okay. Kaitlyn, let me know when you're done, because you might have come in the middle of this here. Have you got all that? Okay. Can I erase, friends? Okay. I'm going to show you how we're going to use this as a sample problem. Suppose I told you Jupiter is about 5 AU from the sun. And now what I want you to do is find the orbital period of Jupiter. Let me walk you through this. We start off with p squared is equal to a cubed. Then we substitute in our 5 AU and we cube it. Now, some of you might actually know what 5 times 5 times 5 is, but if you don't, may I introduce you to the cube key? Okay, I need to do something tricky here. I need to focus. I need to focus close. Let's see. I've got this autofocus button here. Well, that's a little too much. Okay. Do you guys see an orange? This is your backspace key, by the way. 5, 6, 7. Watch this. Doot, doot, doot. So that key's your backspace key, but do you see above it how it's cubed there? So you do 5, shift, and then hit your cube key. That's what you should see. Okay, so 5 cubed is 125, but I know it's blurry back there. This isn't working. So 5 cubed is 125, but that's equal to p squared. Do you guys know how we get rid of a square? That was a stupid thing to do. I'm not going to do that anymore. Let's go back here. You have to take the square root, says Devin. Booyah. We have to solve for p by taking the square root of both sides. So p is the square root of 125. A square root kills the square. Let me get my focus back here. That's pretty good, I guess. Oh, let's back off a bit. Okay. So with 125 still in your calculator, your square root is above here in orange. So you hit shift, square root. What's my final answer? Somebody?
11.
Arunsak, that's too many sig figs. Pardon?
11.
11 what?
Years.
Yeah, this is a magic formula. 11.2 is too many sig figs, Elijah. Elijah, technically speaking, I only had one significant figure going into this, so I would have actually been justified in rounding it to 10, but let's just keep 2 sig figs when in doubt. 11 years, okay? Let's try it the other way. I'm doing many sample problems. Then we're going to switch to our homework. Let me just do one more sample problem with you. Can I erase this here? Okay, I'm racing. One more quick problem here. Pluto has an orbital period of 248 years. Find the semi-major axis of Pluto. This time we're doing the problem in reverse. If p squared is equal to a cubed, then it must also be true that a cubed is equal to p squared. Now, I'm going to do things a little bit differently this time. I always like to solve for my variables and then plug in afterwards. I didn't do that last time, but this time I'm going to do it right. I need to get rid of this cube that's attached to the A. Do you guys know how we get rid of a cube? Devin, what do you think, Devin Irons? You knew what to do before, right? Yes, Devin says a cubed root, exactly. So let's take the cube root of both sides. A will be the cubed root of p squared. Now that I've solved for a, I'm going to substitute in my numbers. A will be the cubed root of 248 years squared. Now I'm going to show you how to punch that into your calculus, okay? Focus, I think a focus of 38 was the sweet spot there. Yeah, 38, okay. Clear it? So let's do 248. First, we're going to square it by hitting our x square key. Boop. That was right there, okay? Now, you guys can see there's a cube root key above the plus minus. So do shift cube root, and that's what you should have. Is everyone getting this? You
Wait,
guys
can you do that one more time? I'm so sorry.
That's fine. That's let's do it from the beginning, okay? We plug in 248 years. Now I'm going to square it. Now I need to cube root, which is up here. So I do shift, and then I hit the cube root key. Is that good? Okay, cool. What should we round it to? Elijah.
40?
Oh, say that? Yeah. We could do 39 AU, Paul. That's fine. In fact, I gave you 3 sig figs. So if you wanted to be nasty, you could even do 39.5 AU. Yeah, Paul, we could have rounded it to 40 or 39. It's probably better to do 39.5. We have 3 sig figs going in, 3 sig figs coming out. It doesn't really matter. 39.5, 40, whatever. Okay. And we're going to be doing 2 problems just like that in our homeworks. Woo, it's homework time. Okay, we can get through this. I'm erasing. Homework. I'm doing that so that I can find it in the video scrubber later, and I'll be able to put a timestamp on that, which was a suggestion from Devlin. Let's go to homework number 2. Find Blackboard. Go to your homework tab. Here's homework number 2. Did you guys want to take a little pause? We did that last week. Did you like that?
Little pause.
Okay, so let's do 10 minutes and then we do homework. Yes, Tiffany likes it too. All right, don't let me forget to start the recording when I come back. I want to pause right here. Okay, we're back. Let's see. I'm gonna set this up and let's get the problems down. I don't know if someone can read me the assignment numbers. I think we have 3 problems. We have 5 problems from 3 different chapters. The first three are pretty hard, and after that, it gets easier. Don't forget to put your name, AS1020, put your section, whatever that is, 002, 00, or 101. If you're a night student, is the audio weird for you guys? Can anyone answer that question? Can you guys hear me okay? I sound okay?
I can.
Okay, so Arunsak, maybe something's going on with your connection? Oh, I fixed it. Cool. All right, that's wonderful. I think what happens when I turn my back, the microphone isn't that sensitive, so I get kind of quiet when I turn my back to you. I try not to do that, but it happens when I'm taking notes. This is homework number 2. I know that we have a problem from chapter 1, 2 problems from chapter S1. No, sorry. 1 problem from chapter 2, 2 problems from chapter S1, and 2 problems from chapter 3, right? Do you guys have those numbers, or do I have to look them up? I just want to sip my oolong tea here.
Chapter 2 is number 59.
Number 59, yep.
Chapter S1 is 41 and 43.
Okay.
And chapter 3 is 53 and 54.
All right. These problems, or first 3 are going to be a whole bit. So let's start. Was that Stacy that was reading that to me? Was that you, Stacy?
Yes.
Are you down to read chapter 2, number 59?
Sure. Its title is
Oh yeah, what's the title?
Eclipse Conditions.
Now hold on a second. Before I let you read that out, I need to tell you guys about the formula you're going to need for this. You've actually already learned this formula, but I'm going to rearrange it for you. You'll remember that you guys learned there's a formula called the small angle formula. And in our homeworks last week, we used the angular size of Betelgeuse and the distance to Betelgeuse to calculate the diameter. Sometimes you actually want to solve for the angular size of an object. Like if you know how big something is and you know how far away it is, you sometimes want to solve for angle. And when you do that, you can perform a little algebra, flip the d over here, flip the 360 and the 2 pi, and you get a formula that looks like this. The angular size of your planet, moon, or star is 360 degrees over 2 pi times the size over the distance. This is still the small angle formula, but this is now the formula solved for angular size. And before Stacy reads us the problem, I thought it might be nice for all of us to get that down onto our page. And because these homeworks, because we're doing them together, these homeworks are going to be perfect study guides for the exam. So you guys are going to be able to follow along and learn from these later on. Stacy, when you've got all that down, you can go ahead and launch into it.
All right. So number 59. The moon's precise equatorial, equatorial, sorry.
Equatorial diameter.
Diameter is 3,476 kilometers. And its orbital distance from Earth varies between 356,400 and 406,700 kilometers.
Okay.
The sun's diameter is 1,390,000 kilometers, and its distance from Earth ranges between 147.5 and 152.6 million kilometers.
How many zeros are in a million again, Stacy?
7. 6.
Six.
Well, sorry.
You'll notice that I put those numbers right into scientific notation. Yes, Star Child, that is a lot of numbers. Remember, this is what it's called when you're solving problems. These are called the givens, okay? And because I've been solving problems like this for a long time, I think it's a good idea to get your givens right onto the page with their units so that you know what you have to work with. It's a lot of numbers, but Devlin, it's also 6 numbers, right? 1, 2, 3, 4, 5, 6. You can handle it. I'm going to give you guys a second to catch up.
Thanks. Okay.
Okay, so I'm going to have to erase this. So, because I need room to do part A, and I'm already kind of out of room here.
Need one more second.
Yep. This is a good strategy for future classes where you may have to solve problems. Always extract your givens from the words and write them down on the page with units. That way you know what you have to work with. Kaitlyn, are you still writing?
All good. Thank you.
All right, okay. I'm going to erase this a little bit. Okay, read us part A if you don't mind, Stacy.
Of course. A, find the moon's angular size at its minimum and maximum distances from Earth.
The trick is going to be to stay nice and organized. A, we're dealing with the moon. We're finding its angular size. Let's start with the minimum distance, okay? The angular size is 360 degrees over 2 pi. What do we have for the diameter of the moon? That's S. What will our S be? Look at your givens. What's S?
3,476.
Units? Yes, Christopher, but the units? Oh, there is. Pardon, Christopher? Oh,
Kilometers?
kilometers. Hey, someone just
That's what I
asked.
said.
Oh, did you? I'm sorry. I apologize, Christopher. I didn't hear you. I think maybe the microphone cut out too fast or something. I don't know. Okay, cool. Hey, someone asked a cool question in the chat, and I want to address it. Devin Irons says, hey, is there a specific word for that similar to aphelion and perihelion? Yes, there is. The terms, I've already erased the numbers, but the terms, Devin, are perigee and apogee. So when we're talking about the moon, we use the terms perigee and apogee. Peri is next to, geo is the Earth. Next to the Earth, far from the Earth. Sometimes people even use apogee in like a literary sense, like they'll say the athlete was at the apogee of his career or something like that, right? It's like the highest point in orbit or the farthest from the Earth. There are terms, Devin, since you're asking, for other planets around other star systems. We call it periastron and apastron or aphastron. That's for when you're nearest to a star and farthest from a star. Okay, so what is, now that we've got some fancy vocab terms, thanks, Devin, what is our perigee distance? What's our perigee distance? Just look at your givens. Tell me what to put. I wasn't expecting this to be a challenge.
$356,400.
Yes, kilometers.
Yes, sorry.
Okay, we have to have a talk about how to punch this into your calculator, okay? It is very possible for you guys to screw up. Austin, does that mean you need to take a picture?
You have to use parentheses.
We are eventually going to get to a point where we want to use parentheses, Austin, but I'm going to teach you how to do it without using parentheses, which is better and faster and cheaper, okay? Let's save the parentheses for when we really need them. But you're not wrong. Here's my strategy, Austin. See if you can follow my logic. When we punch this into the calculator, we're going to do it this way. We're going to do 360. We will divide by 2, and then we will divide by pi so that the calculator knows it's in the bottom. Then we'll multiply by 3476. Then we'll divide by that. Okay, let's do it together. Ready? Follow along with me. 360 divide by 2. Now watch me. Divide by pi. Hit EXP. Times 3476. Divide by 356 400. And then
How did you do?
Devlin?
How did you do pi?
EXP.
Yeah, you just hit EXP. That's it. Can you guys hold them up and let's see how you did there? I'm very curious about this. Kaitlyn looks good. Austin, Caroline, Christopher, Tifany, Ty is good. Jesse, yes, good. Stacy's good. Okay, Elijah, I like it. You guys are doing great. That makes me very happy. Hey, Caroline, what's your dog's name?
I'm lost.
I can help you. Did I ask you this already? I forget.
Ella.
Ella. By the way, did you get your calculator?
Yes.
Okay.
Boom, bam.
Boom. All right. Wait, what, Ella? Yeah, okay.
Yep.
Sorry, you're chilling on the couch. Devlin, can I help there? Want to do that again? Devlin, one more time, okay? You with me? You ready to go?
Got you. Yep.
All right, here we go. 360
Divided by 2.
divide by 2.
Mhm.
Divide by EXP
All right.
times 3476. Divide by 356400. What should we round to?
Yep. I got that same answer. We're good.
Okay, now I've got another question for you guys. An adult question, level 2 question. What is the limiting precision in this equation? What is the limiting precision? Do you understand my words? No?
No.
Okay,
Could it be 3?
let me put it simpler then. It's simpler like, what's the suckiest number? Austin says 4 significant figures. Correct. Austin, these are not measurements. These do not have precision associated with them. They're perfect numbers. But these numbers, as Austin points out, both have 4 significant figures. Okay, Austin, you and I are talking. What should I round this to then?
Oh, that's a great question, Professor. I'd round it to 0.5588 arc minutes, degrees, arc seconds, maybe degrees.
Class, always put the leading 0 in front when you do a decimal point. People are notoriously sloppy about all kinds of things, especially decimal points. 0.5588, and the units are degrees. 4 significant figures. Put a box around it. Okay, second verse, same as the first. Let's do the maximum distance.
For the moon,
For the moon. We're still under part A. So we have 360 degrees over 2 pi times 3476 kilometers. What was the apogee distance? It was 406, 700 maybe?
406,700 kilometers.
406, 700. All right. Show me that you know how to do this and punch that up. Punch them up. Delicious tea. Okay. Anyone? Arunsak gets 0.4897. And what are your units, Arunsak?
Degrees or kilometers?
Watch this, guys. Degrees, that's right. Let me show you what's going on there, Devlin. Kilometers cancel with kilometers, and only degrees are left behind. That's dimensional analysis. And Arunsak, did you round that proper? I didn't punch it in. Did you round that properly?
Yeah, he did.
Okay. Just double checking. Nice. Let's catch up there. Stacy, when you're ready, we'll take part B.
Okay. Part B. Find the sun's angular size at its minimum and maximum distances from Earth.
I'm going to cheat a little bit here. I'm going to do B, sun, and I'm just going to sort of erase the numbers because the setup should be the same.
Is this officially B or is this still A?
This is now officially B, but I had to write all this, so I saved myself some dry erase marker. Now that I teach from home, I got to buy all this stupid shit, and it's annoying. Okay, so I've got to go to Staples today or something. Let's see. The sun's diameter is 1.39 million kilometers. I do remember that. The perihelion distance, remind me, it was 147 point something.
5.
And that's million kilometers. And then 152 point something. 6?
0.6, yes.
Okay, write all that down and punch them up. Looks good, Austin. Austin, how many sig figs we got this time?
3. However, when you round it, it'll only be 2.
Wait, no, that's not how that works. 3 in, 3 out. How do you round that to 3?
0.540 degrees.
Very good. Very good.
Kind of known for that.
I like your moves, son. And I'll take the maximum distance, angular size when you've got it.
I messed up somewhere on the minimum distance. I got 5.32.
Okay.
I don't know what I did.
You want to do it together? Shall we do it together? Ready?
Yeah.
360 divide by 2 divide by pi times 1.39 exp6 divide by 147.5 exp6 equals.
Yeah.
I multiplied by pi, so I
Oh.
got it. I
Watch
fucked
out
up.
for that. That's a really common mistake. Remember, the calculator needs to know that pi is in the bottom. It only knows pi is in the bottom if you hit divide. If you multiply, you end up putting the pi on the top.
Yeah, no, that's what it definitely messed me up. Awesome. Thank you.
Would we want, how many sig figs would we want on this? Because there's a lot of numbers there.
Right, but Devlin, to answer that, you have to look at your inputs. Garbage in equals garbage out. The bottom number, Devlin, has 1, 2, 3, 4 sig figs. The top number has 1, 2, 3 sig figs. Therefore, we only keep 1, 2, 3 sig figs at the end. Same with this next
So
guy.
we're going to keep 3 here.
So what do you get then?
0.539.
0.522.
Yeah, I think 0.522 is the correct answer. So I'm not
Where
sure.
am I getting the 2's from?
Did you multiply by pi instead of dividing by pi?
No, I got 0.539.
Let's do it together.
That was for the maximum distance.
Oh,
Or the
yeah.
minimum.
Okay, I see. Devlin, you're doing the minimum distance, and we rounded. It's what you got, Devlin, is you got 0.5399. When you round that to 3 significant figures, 9 rounds the 9 to 10, or you might think of it as 39 cents goes to 40 cents.
All right. Yeah, sorry, I was doing the wrong one.
That's all right. At least you're getting the right answer. That's what's good. Okay. We can almost put this puppy to bed, but there's a part C. Make sure you get all
Not
that
possible.
down. I'm sorry?
It's not possible.
Oh, you answering part C?
Oh, he's answering.
Can I erase?
Yeah.
All right. Stacy, will you read part C so everyone knows what Austin is talking about?
Yes. Part C is based on your answers to part A and B. Is it possible to have a total solar eclipse when the moon and sun are both at their maximum distance? And explain.
So let's go ahead and let's round back to 2 significant figures. At maximum distance, what is the angular size of the moon? 2 sig figs. From part A, what's the maximum distance?
It's like 0.4897 degrees.
So 0.49 degrees if you round it to 2 significant figures. What's the angular size of the sun?
0.52 degrees.
Okay. And so what is Austin's point?
It's not possible.
Right, because the angular size of the sun is like this, right? And that, the angular size of the sun is 0.52 degrees. The angular size of the moon, what type of an eclipse is this? It's 0.49. What type of an eclipse is that?
A lunar?
Nope. This is these are solar eclipse. Arunsak, it's not a partial. Partial is when it like takes a bite out of the side. Special.
You told us it last class, but I forgot.
Yeah, I wanted to see if anyone remembered what that's called.
I remembered it looked cool.
Yeah, that's good enough. In Greek or in Latin or something, an annulus is a ring. This is an annular eclipse. So to finish our answer, we say, no, a total solar eclipse is not possible as the moon's angular size is 0.03 degrees smaller than the sun, this is an annular eclipse. Okay, that was a bit of a whopper. I knew it was going to be. The next one's a bit of a whopper too. Just giving everyone a second to catch up to me here. How you doing, Donovan? You still writing?
The board's a bit fuzzy. How much smaller is it in degrees?
Oh, 0.03 degrees. Is it fuzzy for everyone? Or is that an internet connection thing? Stacy says it's not fuzzy for her. I just want to make sure my focus is okay. I wrote that really small, Donovan. I'm sorry. I just subtracted this minus this in my head to get 0.03 degrees. All right, here I go. Hey, Elijah, you want to read us a problem?
Absolutely. Just give me one second. I gotta pull it up.
Yep.
Is it the chapter S141?
Chapter S141, correct. Hold on.
Is that the
just
fundamentals of your local sky?
Yes.
All right. So, shit, I got rid of myself.
Local
All right,
sky.
it says fundamentals of your local sky. Answer each of the following for your latitude.
What's our latitude?
42.
Degrees north.
Yes.
Just saying. Okay.
And then it says A, where is the north or south celestial pole in your sky?
All right, hold on a second. So obviously we're going to be dealing with the north celestial pole because we're in the northern hemisphere. Oh yeah, Devlin, thank you. Thank you, Devlin, for doing that. So Elijah, do you know the answer to this one from our lecture today?
Isn't it? Hang on 1 second. I got to look at the
Let me give you a hint, buddy.
north.
Yeah, we want to use the horizon system. So I want an altitude and an azimuth.
Oh, shit.
The altitude would be 90, right?
Nope, that's your zenith.
I think that was when my internet cut out, so I don't know if I have the notes for that part.
Oh, okay. That's actually kind of, well, this will reinforce that, but make sure you go back if you have time and watch that little segment, because I gave you some damn good notes during that time. Conversely, there might be a nice student who's willing to take a picture of their notes and send it to the group through the chat. That could also be, especially someone with really nice handwriting like Kaitlyn, or I can't remember who else has really nice handwriting. Some of you have very nice handwriting. Anyways, what's the answer?
42 degrees?
Which one are you giving me?
For the altitude of the NCP.
And how about the azimuth?
North?
It's north.
That would be 0.
Right. We'll put that in parentheses. The technical azimuth is 0, but north is a plenty good enough description. Okay. When you're ready, Elijah, when you've got that written down, hit us with B.
All right. B. Describe the meridian in your sky, specifying at least 3 distinct points along it, such as the point at which it meets your horizon at its highest point.
So remember that my way of phrasing this is to do the rise, the reach, and the set. So we have a rise, a reach, and a set. And for each of these points, we're going to want an altitude and an azimuth.
The rise would be 0 degrees altitude.
Yep, but a run
It would be-
sec. Yep, go ahead, Stacy.
I'm sorry. The rise is 0 degrees altitude and 90 degrees azimuth or due east.
Guys, you're mistaking this with the celestial equator. The meridian, I shall remind you, is a line that cuts the sky in half from north to south. Hold on. F547. The meridian, my friends, let's choose, what's a fun color? Lime green. The meridian runs north through south. This is your meridian right here. You'll notice it does not rise at 90 degrees, which is east. So try again. 0 degrees in the azimuth.
180.
Careful, Christopher. 180 is south. Okay. This is a matter of taste. And yeah, Devin, yes. But Christopher has a point. Christopher could decide to start south and go north. And it would have been valid for him to say, this is the rise and that's the set. I always tend to have a north bias for just no reason whatsoever, but I'm going to go with north. So 0 degrees north. But I want Christopher to know that his answer would have been acceptable as well. In fact, Christopher, I'm going to use your point as the set point. 0 degrees south. Sorry, and that's 180. What's the reach?
Would it be 180?
Also, there's I need 2 slots here, right?
Yes.
So I don't know which one you're giving me. You're ambiguous.
The reach. Would the reach be 180 degrees?
There is no such thing as an altitude of 180 degrees.
Okay. Then I'm completely lost.
That's
Is the
okay.
reach 90?
Yeah, who said that?
Hey.
Is that because it rises and sets?
Devlin, let me show you why. The reach, the highest point of the, this is the highest point of the meridian. Remember, Devlin, that we define altitude as degrees above the nearest horizon. So from here up to, there, that's a 90-degree angle. Does that make sense? Shoot.
Yeah, so you
altitudes start at the horizon at 0, and they go up to the
and at 90.
Yeah.
Okay, that was my confusion.
How about an advance? Hey, Devin, you're putting your finger on something. No, Devin, there cannot be an azimuth if it's, as you put it, directly in the middle. The zenith is equidistant from all points on the horizon. And Devin's realized that that means the azimuth of your zenith is degenerate. We'll put 2 dashes there because it's a degenerate point, but we can add on the side, it's at the zenith. That's not necessary, but that's to help you guys later when you're studying, okay? The The altitude is 90 degrees. The azimuth is undefined. All right, moving along to part C. Christopher,
All
let me
right.
know.
Shit.
That's okay. Take a second. Wait, Elijah, are you done copying? Is everyone done? All right. Elijah, part C.
All right. Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Okay. Rise, reach, set. And this is straight out of our lecture today. Anyone want to take this?
Could you say the celestial equator rises due east, reaches 48 degrees in south, and sets due west?
That's good, Austin, but you want to help me fill in the technical numbers here just so we can get all hardcore about it? That would be an acceptable answer, but let's do it technical for fun.
Rise is altitude 0 degrees, and the as is 90 degrees or east.
Okay. Keep going.
48 degrees for the reach altitude, 180 degrees / south for the as. And finally, 0 degrees for the altitude, 270 degrees or west for the azimuth.
Excellent. And if anyone had trouble following that, Elijah, we did that today right in our lecture. So he's reading it right out of his lecture notes. Or right out of his break.
Oh, no, I got that part.
Oh, okay, cool. Okay. I'm going to have to erase this in a moment so that we can do D.
Bless you.
Or as my friend likes to say, when you die, nothing happens. So, okay, here. I'm going to erase this. All right. What's D say, Elijah?
All right. It's does the sun ever appear at your zenith? If so, when? If not, why not?
What do you think the answer to this is? We talked a little bit about the motion of the sun today. What y'all thinking? Austin, let's take a peeks at a little picture that you saw in today's lecture. Let's take a peeks. I need the astrometry. Yeah, this picture here, slide 9. According to this, now, this is not necessarily set to our latitude, but it looks similar. Remember that on the day of the spring or fall equinox, the sun travels on the celestial equator. Let's see what the chat says. Austin, at noon, the sun is on the meridian, okay? Oops, I was trying to get a circle there. At noon, the sun is on your meridian, but that does not mean it's at your zenith, right? You see what I'm saying? This is the zenith up here.
So the answer would be no, it doesn't.
Yeah. What would the altitude of the sun? I'm going to ask you a couple of questions here. What is the altitude of the sun at noon on the spring equinox? What is the altitude of the sun at noon on the spring equinox? That sounds crazy, but you know how to answer that. What's this angle?
60 degrees.
No, 48, says Austin, right? Is that
42.
No. Remember me and Kaitlyn had this thing earlier where she said 42? This is the alpha angle from alpha, beta, gamma, delta. So this angle here is 48. Okay, the day when the sun is highest in your sky is noon on the summer solstice. Can any of you tell me the altitude of the sun at noon on the summer solstice? In other words, forgive my crude drawing here. Where do I set the thickness of this line? I thought I could do that somewhere. What is this angle that goes from here up to here? Can you do that one, Austin? What is it?
My guess is either 42 degrees or 72 degrees.
71.5 technically, but you had the right spirit. Remember that the declination of the sun, the highest the sun gets on the globe, is positive 23.5. The ecliptic makes a 23.5 degree angle with respect to the, let's see what's going on in the chat there. I'm, fudge, clear. Chat keeps like, it's 71.5. Let's just take a look and see how I did that, okay? The celestial equator is 48 degrees. This is south, right? And this is north. The sun, its maximum angle that it can make, this angle here is 23.5 degrees with respect to the celestial equator. No, the sun cannot reach the zenith in the Rhode Island local sky, but only reaches a max altitude. Look how many fancy vocab words I'm using. But only reaches a maximum altitude of 48 degrees plus 23.5 degrees equals 71.5 degrees at noon on the summer solstice. Forgive my abbreviations there. I want to see if anyone out there is really good. Thought question while you're writing this down. What is the maximum latitude that you, oh, that's cool, Devin. By the way, I don't know if you know about the famous Greek philosopher Eratosthenes, but he actually used the shadow of a stick to measure the circumference of Earth in like 400 or 500 BC. No, maybe it was 380 BC. Like this guy used two different he put a stick on the summer solstice in two different cities, and he measured the angle on the shadow of the stick to calculate the circumference of Earth. That's really cool. No shadow. I like that comment. Here's a comment for you. What is the maximum latitude you can go on Earth and still have the sun reach the zenith? Obviously, if you're on the equator, the sun can reach the zenith. Hawaii, I think, is like 15 degrees above the equator. So we know it can reach it at Hawaii. How far north can you go and still have the sun hit your zenith? Anyone want to take a guess? This is a challenge question.
Can you repeat the question?
Fair. First of all, let's just make sure everyone understands this part. If you are on the equator, the sun can reach your zenith. Arunsak knows. Arunsak, you devil, you. The question was, how far north can you go and still have the sun reach the zenith? You can see it from Hawaii at the zenith, but you can't see it from Rhode Island. Arunsak figured out that the maximum latitude is 23.5 degrees north. You are the chosen one, Arunsak. Also known as the Tropic of Cancer. Likewise, the Tropic of Capricorn, 23.5 degrees south, is the lowest you can go and still have the sun reach your zenith. This is sort of what defines the tropics on Earth. The tropics are those latitudes. The tropics are those, I'm just laughing at the chats, they're great. The tropics are those latitudes where the sun can actually get overhead at high noon, so to speak. Okay, one more question. Let's do part E.
Part E. Okay. What range of declinations makes a star circumpolar in your sky?
This is also a challenge question. Range of declinations that are circumpolar. Okay, first of all, range. The range means two numbers. So we want our declination to go from some minimum value to some maximum value. I also need you guys to remember what declination means. You've probably, I already know that most of you have forgotten what declination means. I think I asked you, we're all star children, yes. Christopher, do you remember earlier we talked about this at the beginning of class? We looked up the definition, or you knew what the definition of declination was. Do you still know?
I can look in my notes again.
Star Daddy, I like that one. Totally not going to get fired today. Maybe I'll try that one out at the bar. We'll see if it works. I'm sorry, Christopher, I got distracted in that joke. What was your definition again? Or anyone? I don't.
I'm looking. I can't read my own handwriting.
Declination.
Okay, I got it.
Okay. Degrees north or south from the celestial equator.
A small issue. We use positive and negative rather than. Once you're in the sky, it's customary to use positive and negative. That's just tradition. Okay. So all right. Then let me ask a simpler question than this one. Can you guys tell me what the total range of declinations are on the celestial sphere? It's positive or negative from the celestial equator. What is the total range of declinations that a star could have on the entire celestial sphere?
180.
That's the interval, but I need two numbers for a range, right? Let me explain some mathematics terminology. This is a coordinate. This is a number line, right? Coordinates are when you pick a number, 10 centimeters, 20 centimeters. An interval is the distance between two coordinates. For instance, if I have a coordinate 30 and a coordinate 10, the interval between them is 20, right? So what Devlin just gave me there was an interval. I'm looking for a range for two numbers, minimum and maximum. What is the total range of declinations that a star could have on the celestial sphere?
0 to 90.
You can do better. Yes, Austin. Negative 90 at the south celestial.
Oh, come on.
I know. These to positive 90. I know. Okay. We got to do this. Now, listen. I know that this is going to screw people up because I've been teaching this for a long time. Here's what we're going to do. We're going to take this picture here, and you guys can see my screen, right? Let me go to slide 47. Let's try to label some declinations on this. We have to kind of do this as as a precursor to solving the problem. So guys, work with me here. I'm going to try to write it out with my pencil in red. What's the declination here at the celestial equator? You might even want to label this
0.
on 0 degrees. Good. What's the declination here at the North Celestial Pole? I like to use
90.
positive 90. Good, Christopher.
Positive 90.
Positive 90 degrees. What's the declination of our zenith?
Positive 45.
Not 45 for the Rhode Island local sky. What's the angle from here to here? Someone chats it. Not 48. The zenith.
Is it
this,
30?
No. Somebody knows this. Yes, Austin, 42. Positive 42. Okay. Now, I want to show you a picture from our book, but I don't have an Does anyone have an electronic version of the book?
I do.
Who said that?
Me, Devlin.
Oh, Devlin, is it possible for you to call that up on your computer?
Give me 2 seconds.
Well, you know what? Hold on. No, let me keep this simpler. I'm going to just show you from the book itself, okay? I want to show you guys a really beautiful picture of circumpolar stars. It's the opening photograph of chapter 2, and I think it's really well done. It would have been nicer to the opening of chapter 2 shows a picture of circumpolar stars as seen over the Arches National Monument, which I think is in Utah. It's this legendary park. And someone did a very clever thing. They stood at the right distance from the arch and pointed their camera towards Polaris and left the shutter open for several hours so you could see the circumpolar stars. Is every star in this picture circumpolar? No, says Caitlin. Caitlin, which ones are circumpolar? Oh, it's in Moab, Utah. Have you been?
No, I've never been, but the ones that are circumpolar are the ones that you see like going in almost a full circle, not the ones that you see going below the horizon.
Right. Now, let's start with Polaris. Is Polaris circumpolar?
You betcha.
What's its declination?
I do not know.
Here. Yes, you do.
About 3 degrees.
Sorry, say that again?
About 3, right? Or 2.5.
Wait.
Okay.
This is where I think someone said it, but this is where Polaris is, right?
90 degrees.
Positive 90, good. Can there be any declination greater than positive 90? No.
No.
So we know what our max is. Polaris. Okay. Now try to think about what the last circumpolar star is in this picture here. So Caitlin's correctly identified that the stars inside the arch, or at least these guys, are circumpolar. Let's look at the very last circumpolar star that we see. The last circumpolar star is this one here. What makes this the very last circumpolar star? What is it doing that none of the other circumpolar stars are doing?
It's close to the ground.
It's touching the horizon, Devin. Beautifully said. In which direction, Devin? It's touching the horizon. In which direction? What direction is that? You should know.
West.
Jesus. This is kind of like
no
what
idea.
color is an orange? It's north, Arunsak says. That's the North Star, right? It's north. Okay, so work with me here. This is a tough problem, and tough problems require hard thinkins. So the very last circumpolar star then would be this star here. I'm going to make it blue for star. It's the star whose circle just barely grazes your northern horizon. In other words, these stars are all circumpolar, all the stars that are kind of hovering around Polaris. And the very last circumpolar star, sorry, my circles are kind of crappy here. It's hard to do this with a mouse. The very last circumpolar star is that one which grazes the northern horizon. If I only knew the declination of my northern horizon, that's a challenge question. What is the declination of your northern horizon?
Is it 42 degrees?
Unfortunately, no. This angle is 42. It might help to remember that the celestial equator also extends down here, right? The declination is how many degrees?
Oh, 90.
Not 90.
Then I don't.
Someone's chatting here. Nope, nope. I should have drawn a better picture here. No, there's no. Okay. Here. This is your zenith. This is north. That's the north celestial pole. The celestial equator goes like this. This is the celestial equator. You're supposed to know what that angle is. I see a square. What's this angle? 42.
That angle is 42.
But this is the declination of your northern horizon. It's how many degrees up from the celestial equator. Have I lost you all? You guys all look, or are you
My
zapped?
best guess is 90. I don't.
I'm sorry, say that?
90.
I can tell you what the answer is, but the question is, are you going to understand it?
Absolutely not.
Look, this declination is 0 degrees. The declination of your zenith is positive 42 degrees. The declination of the north celestial pole is positive 90 degrees. You know this angle is 42 because you just said it. What's the angle from the celestial equator up to your northern horizon? I'm giving it away. I'm giving it away.
48.
Thank you, Arunsak, Star Child. Positive 48 degrees. And that's our answer. I know. That was a lot. I'm going to give you the answer to E a little faster than that one. I made you work a little bit. It's important to look at this picture here. We just discovered, let me just review what we learned here. We learned that the circumpolar stars, the stars that never set, I know, it's tough stuff, are stars that go from a declination of positive 48 degrees to positive 90. The next question is going to ask us about, I call them anti-circumpolar stars because I don't know what else to call them. Stars that would be like at the south celestial pole all the way up to here. These stars never rise above your horizon. They're like the opposite of anti-circumpolar star, or they're, yes, circles are important. Let's just have, Elijah, you were reading. Can you just read me number E real quick? Sorry, number F real quick.
Absolutely. It's what is the range of declinations for stars that you can never see in your sky?
Anyone want to just take a guess at it? Just use your
0 to 48.
Sorry?
Would it be 0 as the minimum and 48 as the maximum?
No, because 0 degrees is the celestial equator. And as you can see in this picture here, the celestial equator will clearly rise above our horizon.
So then it's anything below.
Devin's got it. And so does Paige. All right, nice to hear from you, Paige. Negative 90 to negative 48. Very good. We should start here for the minimum, though. It goes from minus 90 to minus 48. I'm betting a large number of you out there are feeling a little seasick from all this. I can understand this can be a little much at first, but it doesn't hurt you to stretch your brain and to try to think about these problems. It's good for you. There is a eureka moment where it all kind of snaps together, but you have to work to get there. Let's just see if anyone follows me. Suppose you're at the North Pole. What are the range of stars that are circumpolar? What's the declination range? What are the ranges of declinations of stars that are circumpolar from the North Pole? Not correct, Austin. You're wrong by one number.
Maybe 0 to 90.
Yes, Devlin, Star Child. 0 on the horizon.
90 in the zenith.
Yeah, you know what's interesting about the North Pole? When you get to the North Pole, declination and altitude become the same thing. Let me just explain that once again for anyone who might have missed.
And that's because the sky can only be above you at that point, right? Like there's
All stars are circumpolar from the North Pole, right? So that was 23, I think. Shoot, 23. So yeah. So what Devlin just said is the stars that are circumpolar go from, they're all of them from your horizon here. Now the altitude is 0 to 90, but that also happens to be declinations. Declination of zeros at the horizon, declination of positive 90s overhead. Okay. Austin, your answer would have been correct if we had gone to the equator. If you go to the equator, the range of declinations would be negative 90 to positive 90. You'd see all stars from the equator. I'm sorry. Wait a minute. If I asked it the exact same way, no stars are circumpolar from the equator. All right, whatever. I think I've beat that question to death a bit. Let's move on. The next few questions should be easier now that we've done that. Okay, Kaitlyn, are you down to read us number 43?
Oh, show. Let me pull it up here. 43?
Yeah.
Local path of the sun. Describe the path of the sun through your local sky for each of the following days. Do you want me to go on to A?
Sure.
The March and September equinoxes.
All right, let me help you guys set this up. We're going to describe the path of the sun on a few key days. For each path, we want to have a rise, a reach, and a set.
Okay, no problem.
And we want an altitude and an azimuth. We're starting off on the spring and fall equinoxes. Let me show you a slightly jazzier picture. A share screen would go a long way here. Share screen. Escape. Astronomy 1010, astrometry. Remember, friends, that on the day of the spring equinox, the sun is located at the celestial equator. So here's a cartoon, a nicer cartoon, showing you what we're doing. We have to describe the path of the sun on the spring or fall equinox, rise, reach, and set. Can you do it? This is for a Rhode Island local sky.
A particular account will first show all transactions. When you scroll down all the way, it will show you Bank America.
Caitlin, how good are you at foosball?
Above that is your account
Is that
number.
what that is?
You press two,
Yeah.
and it does also show your
Not that good.
Oh.
Never played it, really.
Damn, I think with all this COVID quarantine, you'd be on that, rocking that thing every day, but okay.
No,
Anyways,
the test that I use is,
sorry.
no, go ahead, no worries.
I'm just distracting you guys. Anyways, what do I do here? Does anyone know what to do? Austin, oh, yeah, I'd say so. It's probably fun. Anyways, does anyone know the path of the sun in the spring equinox? Here's a hint, big hint. It's the same as the path of the celestial equator. Psst, see the previous problem, part C.
I know the answer.
Okay, give it to me.
All right. Rise 0 degrees, 90 degrees east.
Let's just use directions for this one. Oh,
Okay.
I'm sorry, Elijah. I took a little bit of time. Elijah, can you watch the last two? The last two problems are really simple. They're Kepler's laws.
Que te va bien.
Nice. Can you watch the last two later and then turn it in later, Elijah? Is that okay? All right.
Yeah, no problem.
Yeah, we'll see you. The last two problems, guys, are going to be super fast. So let's just stick to directions for azimuth. That'll make this problem go smoother and faster. So hit us, Austin. What do we got? 0 degrees east. What is it?
Degrees and east. I mean south.
48 degrees south.
0 degrees west.
All right. So that's the path of the sun on the spring or fall equinox. Jack, that sounds good. The last two problems I was saying are real simple, so just watch it. It'll take you like 10 minutes to do the last two problems. This is a tougher homework than the average homework we do in this class, so don't feel bad if this is a lot. Kaitlyn, hit us with part B.
One second. Okay, part B, the June solstice.
In other words, the summer solstice. Okay, so Austin helped us crank out that last one. Let me show you the picture here. Okay. Share screen, path of the sun. So now we're trying to do this. We're trying to go, I'll use yellow for the sun. In fact, you know what? This picture is kind of nice in terms of like design, but I think this is a better picture here. So here is, this is the rise, that's the reach, and this is the set. Anyone want to try to tackle this one? Well, look, the first question should be easy. What is the altitude of this point? You should know the altitude automatically, right?
0.
Yeah, because it's on your horizon. So we know it's got to rise at 0 degrees altitude. What direction would you say this is? Here, what's this?
East.
When I think east, I think here, but you'll notice that it's actually rising.
Northeast?
Yeah, we'll say northeast. In fact, oh gosh, do I want to tell this to you guys?
No.
Yeah, you're right. Okay. All right. North of
Not today.
Fair. Okay, what about the reach?
North of east.
Yeah, it's not. I don't want to say northeast because it's not due northeast. It's north of east.
Okay.
They can't. How about here? This is your reach. What's the altitude? We actually did this one earlier, remember? In the previous problem, we calculated this angle. Now, 71.5 Arunsak. I believe 48 plus 23.5. Yeah, but close enough. It's 71.5 degrees. Arunsak, anyone? What's the direction?
South.
Good. And how about the set?
South.
Zero
Would that
degrees?
also be 0 degrees?
And south of west. Sorry. No, not south of west, Devin. Look at the picture. It's north of west, right? It sets here, which is north of west. Okay? All right, cool.
That's a little better, Professor, that picture. That makes sense.
Yeah. The diagrams can help you. The diagrams also, like, I think this
Would
is
this-
something, I think this is something we should know about. Like, it's the fucking sun. Every day it gives us warmth. We should understand how it moves through the sky. That's like part of being alive on Earth.
Would this class be a lot easier if we were in person?
I don't.
100%. 100%.
I've been wondering that, and I'm not sure. You know what's kind of cool about the Zoom thing is
We have a lot of time. We get to do all the homework and stuff here, but
My
I
sister
still
took your class in person. She said it was hard, but she,
Wait,
I
who's
think she passed
your
it.
sister?
Yeah, my older sister,
Oh, cool.
Marina Landry. It might have been Porter.
Recently or a long time ago?
She said it was like 3 years ago, maybe, if
okay.
not longer.
Look, the class is hard, I suppose, because astrophysics is hard, right? This isn't basket weaving or like QuickBooks 101. It's astrophysics. So, but it's not that it's hard. It's that you're just doing different kinds of things. You're thinking about different things than you're used to. In fact, here's my take on this. Once you get used to a class like this, other classes don't hit as hard and they don't feel as good. You get addicted to it. You'll see. Also, it's interesting stuff, and you'll be surprised. You might think, wow, this is kind of useless. I'm never going to need to know the path of the sun. You're so wrong about that. This stuff will pop up in your lives in weird ways that you don't expect. So it's hard, but we're doing it together, and that's making it easy. Okay, part C.
Are we gonna do it together on the test and quizzes too, I assume?
Well, I'm not giving you any quizzes, and I'm giving you 2 tests. And let me say this about the test. You have to do it on your own in the test, but you know what I did during the summer, which actually, I treat the test as like a full contact sport. And when we're in person, I would like pace around the room, and like if people got stuck, I'd give them passive aggressive hints and stuff, and I'd give you little hints. So I did this in the summer, and what I had us do is when we took the test, just like we were in class, everyone kind of logs in the square and we all mute. And I just sit there at the desk, you know, reading or grading or whatever. And then if you have a question, you can ask me and I'll give a hint to the whole class. So you do have to do it on your own, but I'm not above giving you a little push, because sometimes you just need a little push and that gets you rolling, you know? So
Maybe like a big.
Sometimes I give big pushes. Okay, well, anyways,
All right.
I don't want to spoil all my secrets just yet, but in a way, we will do the test together. It will be a little more independent, though. The test is going to be the scary part. You will be, all of these questions, these are the types of questions I'm going to ask you on the test, and you will be ready for them because you will have practiced. Okay, part C is the winter solstice, right, Kaitlyn?
Yes.
All right, let's see if anyone's getting better at this here. I'll show you the picture.
Let's see what we got going on.
What do we got? We got a little bit of this. There's the rise, a little bit of that. That's the reach, and a little bit of that. That's the set.
All right.
You want to try that, Austin?
I do.
All right.
All right, so altitude for rise is 0.
Avi? Direction?
And for set is 0 as well.
Correct.
And now for reach, my guess would be 23.5 degrees?
Almost. Check it out. The celestial equator is at 48 minus 23.5, which is the ecliptic, 24.5. But you had the right idea. And how about the directions?
All right, so can you go back to the picture?
Yes.
Thank you. So then for rise, it would be south of east.
Correct.
It would be south for
Correct.
reach, and then it would be south of west.
Beautiful. Nicely done. South of east. South.
And now we're done. We did all the homework.
No, we got 2 more to do. Actually, there's also a part D.
I thought.
This is a bad homework. A bad homework takes a full 2 hours to do as a group. A good homework can take like an hour and 15 minutes. I'm not going to lie. Today's one of the bad ones. It's just,
This is torture.
I know, you know what? Be tough. You know what's torture? Working a shit job for the rest of your life. That's what's torture, okay? So
True.
this stuff is fun, okay?
You got approval for my house.
Now, is there a D, Caitlin? Did I task us with part D?
Yeah, D is today.
All right, so how are we going to do this? Would you guys have any idea how to guesstimate it today? We can't.
Well,
It's
we are
cloudy. Devin says we can't do it. It's cloudy. If you think about it, guys.
Close to the fall equinox, though, right?
Yes. So that's one way to do it, is to say we're close to the fall equinox. Was that Christopher I heard there? Good thinking. Christopher, if we want to be real gangster about this, what we would do is we would look up the declination of the sun today. The declination tells, these are all tracks of constant declination. So I happen to know that we can get the sun's declination a couple of different ways. The cheesy way is we'll go to sun to Sedna, and that brings us to ephemeris.com. And they usually give you the declinations of the sun and the planets. The declination is 4 degrees. So that means if we go back to this picture here, it's really close to the fall equinox, but it's just a little bit about 4 degrees. And that's the path of the sun.
52 degrees.
Let's see, 48, yeah, 52 degrees. Good. That's going to be this.
Everything else would be the same for whatever the spring fall equinox.
He's totally right, right? So the rise is 0 degrees just north of east. It's 52 degrees because he added 4 plus 48, and that's south. And then the set is 0 degrees just south of east. Just north of east. In fact, I believe our next class the fall equinox, or no, 2 classes from now. The fall equinox is on the 22nd, a week from Tuesday. Okay, let's crank out the last 2. I think we can do it.
Isn't set supposed to be just north of west?
Oh, yeah. Sorry. I was just testing you. Congratulations, you passed the test. Okay, just testing you. That was last night's whiskey talking there, okay?
Yay, whiskey.
I did bad last night, friend. My friend came to town, and let's just say it was rough. Okay, let's do these last 2 problems. Chapter 3, 53 and 54 are a breeze. Kepler's laws, we already learned that. I'm erasing this. All right. Chapter 3, number 54. Star Child, Star Children. Devlin, you want to read that one?
1 second. I have to pull it up. I don't have the homework questions up.
Aren't we doing 53 and 54?
Yes, 54.
I think 53 we already learned, right? That's what you said?
Yeah, this is going to be a breeze.
All right. So 53 or 54 I'm reading?
53.
A newly discovered planet orbits a distant star with the same mass as the sun and an average distance of 112 million kilometers. Its orbital eccentricity is 0.3. Find the planet's orbital period and its nearest and farthest orbital distances from its star.
Okay, first of all, they told us 112 million kilometers. How do I turn that into a right proper number? Thanks, G. Times 10 to the 6. I just wanted to make sure that y'all remembered, right, Stacy, that a million is 10 to the power of 6. We want to drive that home. The orbital eccentricity is 0.3. We have to do 3 tasks here. We have to find the period, And then we have to find, let's bust out some fancy vocab, Devin. What do you say? Find periastron, because it's not the sun. Periastron and aphastron. That's some cool vocab there. And I picked that up from I've got some book on orbital dynamics, but that's not going to interest you guys. Okay, what do? I'm stumped. Why'd they give us the average distance? What does that have? What formula do I want? Does anyone know what to do? Caroline, you're dying to contribute, right? You're trying to.
Okay, so
P2 equals A3?
Hell yeah, Austin. P squared equals A cubed is our man. Now, we got an issue though. Remember that A is the semi-major axis of the ellipse, but it's also the average distance. In other words, they gave us the semi-major axis of the planet's orbit. By giving us the average distance, they've given us A. However, we can't plug it into the equation yet. Why not?
Because of E.
Yes, Devin says AU are required. We absolutely do. Every formula is like a little monster, okay? You got to feed the monster what it wants to eat. This monster wants to eat years for period and astronomical units for distance. So, Devin, what are we going to do then? I don't know what to do.
compare it to the distance of the sun, right?
The conversion thing, says Arunsak.
Yeah.
Yes, the conversion thing. And what do we call that technique that we use to do this?
Angular
size? Something.
The angular size? Is that a hit or no?
No, that's a formula. We're looking for a conversion technique. The technique that we always use.
You do the 112 times 10 over 6 in a times and then a division sign.
Yeah. Okay, cool. So you know what to do anyways.
And now you want kilometers on the bottom and AU on the top.
Hell yeah. Okay, this is called dimensional analysis, by the way.
Dimensional analysis. I knew it was something.
There are many different levels to dimensional analysis. As the class goes on, I will take you deeper and deeper down the rabbit hole, okay?
So then we want 1 AU on the top, and then we know the distance of the sun from our notes. I don't know it off the top of my head, but that's what you want to put there.
Anyone remember it?
Give me a second, I got it.
I once told one of my professors, oh, it's not important to memorize it. You can always look it up. And then he looked back at me and he said, yeah, but if every time you have to look up 2 + 2 = 4, you're kind of screwed at life. Okay, so.
Man, it's way in here. I have no idea.
Average.
Would it be 2.5 million kilometers or, yeah?
Just a moment. The answer is about 149.59802296 billion meters.
It's meters?
Yes.
I don't
Yes.
want it in meters. Wait, is someone Googling or was that?
1.49
Alexa.
96 times 10 to the 8 kilometers.
Oh, it's 2.5 million light years, I think, right?
Austin, you're not wrong. 150 million. 150 million.
Oh,
Okay.
jeez.
I predict that you will all have that memorized by the end of the semester, whether you meant to or not, okay? Okay, so punch them up.
Oh, that's a nice number.
Yeah. What do you get?
1.34 AU.
No, it's 112 over 150.
Holy shit.
It can't be bigger than 1. It's 112 divided by 150. 2 sig figs works for me if that works for you.
I don't even want to say anymore. I'm embarrassed.
Oh, no, that's all right.
0.75.
Correct, Christopher. Arunsak, you lost a decimal somewhere. 0.75 AU. Okay, now we can plug it into p squared. Oh, yeah. Do you want to, Arunsak, check me out. 112 divided by 150. Boom. All right, now we can plug it into p squared equals a cubed. Let's put the square root on the other side, okay? So eraser, p is equal to the square root of a cubed. I like to solve it algebraically before I put the numbers in. And that means we have the square root of 0.75 cubed. Can you guys want to see if you can do that without my help? I taught you earlier. Let's see if you remember the techniques.
Uh, 0.65 years.
Nice. Nicely done, Christopher.
I forgot where the square root button is.
Sure. Why don't I help you guys? Because there's probably a few people who forgot that method. Devlin, watch. 0.75. The cube is above the backspace, so I'm going to hit Shift, backspace. Now I got a square root by doing Shift x squared.
Okay.
Cool. We also have to find the periastron and the aphastron. I'm going to go up here a bit. Remember the formulas. Perihelion or periastron is A times parentheses 1 minus E. Aphastron is A times 1 plus the eccentricity. So let's just, can I erase this?
1 second.
Sure. I'll set up the peri. 0.75 AU times 1 minus 0.3. Class, before you punch that in, can I walk you through my technique for doing this? It's really easy, but I want to set some good habits right now. I just want to get you guys familiar with how your parenthesis keys work. So just hold on a second. Let me get my focus doodah up to like 38, I think was like a good spot. Okay. I want you to just watch me do this, okay? So I've got 0.75 AU times open parentheses, then you do 1 minus 0.3. Now watch this. When you close the parentheses, it does the parentheses, and then you hit equals. Everyone try that out to make sure that you could, because later on I'm going to want you to use parentheses in a more advanced context. So I want to get you guys familiar with it now. What's my final answer? Two sig figs. Units? Devin got the answer. What are the units, Devin?
AU.
Good. Box it up. I'm going to erase this part now. Aphielions equally easy. 0.75 AU times 1 plus 0.3. Go ahead and punch that one up for me.
0.98 AU.
Nice. That takes care of 53. I'm gonna eat the biggest, baddest tomato sandwich after this office hours. I can feel it coming. It's tomato season. Can I erase everyone? We got one more problem between me and my tomato sandwich. Chapter 3, number 54. Ooh, that sounds good. All right. 54. Anyone? Emily, are you down to read? I just saw you there.
Yeah, I can. Hold on, let me pull it up real quick.
Okay. This next problem is basically almost the same as the last one. I think it's about Halley's Comet. By the way, did any of you?
Little necks are so good.
Little necks are, actually, I have a confession. I don't eat seafood because some of it makes me really sick, but I'm really depressed about it because there's so much good seafood in Rhode Island. It's like, if you're going to eat seafood, this is the place to be.
54.
Yeah.
Meridian crossings of the moon in Phobos.
Oh, squad. I think you might be in
Is that on the wrong one?
Chapter 3.
Oh, okay.
Whoa, you were a caw hogger? Devlin, I had make this joke in my 1010 class where I talk about tides, and I'm like, every good caw hogger knows that there are neap tides and spring tides. That's great.
All right. Halley orbit.
Okay.
Halley's Comet orbits the sun every 76.0 years and has an orbital eccentricity of 0.97.
Okay. And what does it want us to do?
A says find its average distance from the sun, semi-major axis.
Remember, that's A. So we're going to use A cubed is equal to P squared. I've flipped it here. Lots of heavy lifting in mud. Devin, I'll send you guys a song while you're calculating. You can listen to after. Okay, so what we're going to do is we're going to do A cubed. A is the cubed root of P squared. And that's the cubed root of 76.0 squared. You guys want to see if you can do that? Remember that your square key is here. To get your cube root, you've got to go shift plus minus. Let me know when you get it.
I got 18.
Yes. What are the units?
That would be AU.
Excellent. That one's going out to you, Devin. 18 AU.
Can you please do that?
Yeah, can you do that on a calculator? I'm confused on how you got that.
Sure.
Thank you.
Let's see. 76 squared. 76 .0 if you feel like it. There's your square key. Boop. I know, that's a great tune. Now we're going to cube root it. So shift cube root.
Oh, I was doing it backwards.
Yeah, well, the order isn't important, but I think what you meant by backwards is you might have hit cube instead of cube root or something. Watch out for that. You could do the cube root of 76 and then square it. By PEMDAS, exponents are equal in priority. Not to get all PEMDAS on you, but it's a thing. Okay, part B, Emily, when you're ready.
Okay, sorry, I had to unmute myself.
Sure.
Find its perihelion and aphelion distances.
All right, so our peri is A times 1 minus E. Our A was 18 AU times 1 minus 0.97. Go ahead and punch that for me.
What was the unit for the last problem?
It was AU, right? That was the answer to the last problem. Stacy, what do you got?
0.54
That sounds good. What are the units?
AUs.
Killer. All right, and now the aphelion. 18 AU times 1 plus 0.97.
35 point.
I'm going to address Daniel's question in a sec. Chris, hold on 1 second. It sounded like someone wanted to see how that happened, and I'll show you. Daniel asks a cool question. Wait, isn't it 3 significant figures? Yes. But Daniel, how many significant figures does this have? 2. So the eccentricity is actually polluting our answer. Eccentricities are measured quantities, and they have precision associated with them. In fact, sometimes...
How do we get to 0.54, though?
Sure. Watch my moves. We're going to use parentheses, Devlin.
Oh, so we're using the distributive property. Right?
Yeah, whatever that's called. Look, no, we're using the parenthesis keys. That's what we're doing. 18 times, open parentheses, 1 minus 0.97, close parentheses, then equals.
Okay.
Make sure you can do that yourself.
I was doing 0.92. It looked like a 2.
Oh, yeah, sorry. Sorry, that's my bad handwriting.
So I would have had the right answer. I was just confused. Sorry.
Okay, that's cool. And Christopher, what did you, oh, sorry. What the hell? Christopher,
35.46 AU.
Well, that's
or would it just be 35 AU?
Yeah, 35 AU is cool. Honestly, when in doubt, sometimes I just round to 2 for fun. It's good to know the rules and then break them, you know? Yes, it's tomato sandwich time. Okay, that was a hell of a homework, I know, guys. Yeah, so, hey, can I say a couple of things? I don't think I need to do the whole watch everyone submit, because we kind of know how to do this now, more or less, right? I'll stop the recording in a second, and I'll hang out for a moment if you guys want to ask me questions, or if you do want to see me submit your thing. You know what I discovered working with the 1010 students yesterday? I was under the impression that those hyperlinks in the homework submissions, I was under the impression that they show up if the image dimensions were too big, but I experimented with a student. We like changed the size of his file up and down, and he kept getting those hyperlinks. Now, most of you have figured out how to upload your homework so that it appears in the preview box, but a couple of people are still giving me the hyperlinks. I wrote the Blackboard manager at CCRI an email to be like, what the hell is going on here? Because there's so many of you and so many papers to grade, it would be nice if we could avoid the hyperlinks and I could just open your, you know what I'm talking about, right? When I see the little
Can I
preview
make a
box.
suggestion?
Yeah.
I don't know if mine went through or if you saw them, but if you put all the pictures in a Word document, it should always appear in the preview.
Oh, that's a cool idea. So I'll have the students who are having trouble with hype. That's a great thought, Devlin. So are you sure about that? Always in a Word document?
Well, if you want to check mine real quick, you could. That would be a solution. My Chapter 1 lab and my Chapter 1 homework are both submitted in Word documents.
Needs grading. Devlin, what's your last name again?
Anderson.
So let me, okay. Let's see here. Oh yeah. So you took this photo, but then you put it into a doc, huh? That's a really cool solution to this problem. Did everyone hear that? That's actually really important because the same way that I saw that preview. Now not everyone needs to do that. Most of you are doing just fine, but there was like a couple of people who still had trouble with their submissions. So I don't know, work it out, see if you can make it good. Before I stop the recording, any other questions that I should keep in the recording here? Or?
Would I just be able to copy down the last answer? It's behind you.
Yep. Going forward, we're going to meet on Tuesday, lecture and the lab. Please, class, if you can, if you're crafty, get yourself for Tuesday's lab a piece of cardboard, 2 push pins, and make a loop of string. I think it's about, cut it to twice this length. This loop of string is 15 centimeters. So cut a loop of string that's like 30 centimeters and use your best knot tying skills to tie it into a loop. That'll be nice, and have a ruler too, if you can do that. If you can't get those materials, you're gonna have to freehand it. It'll be a little awkward, but you know, those things aren't hard to come by. Okay, I'm going to stop the recording.